Hello. Good morning, everyone. Welcome to the day 4 of the 76th annual session of the Indian Institute of Chemical Engineers IICHE-CHEMCON 2023, organized by IICHE Headquarters, Kolkata, in association with Rajiv Gandhi Institute of Petroleum Technology, Jadavpur University, and Heritage Institute of Technology, Kolkata, themed on energy transition, challenges, and opportunity. To begin with today's serious lecture, we have in the beginning CSIR NEERI ChemCon Distinguished Speaker Lecture Award. For this, we are honored to have among us Professor A.B. Pandit, Vice Chancellor ICT Mumbai. He was an instrumental in starting a majority activity and program in the area of hydrodynamic cavitation for intensification of physical and chemical processing applications. He has successfully exploited the cavitation phenomena for various operations such as crystallization, emulsification, nanoparticle synthesis, and process such as esterification, oxidization, etc. on the industrial scale. A unique creative approach of using fundamental knowledge coupled with simple, elegant experiments has resulted in novel gravitational reactors. His intuitive ability and capacity to create new knowledge have been demonstrated by his over 456 publications, which have received over 36,049 citations with an H index of 102 as per Google Scholar, which is probably the highest for a chemical engineer working in India. Six books and over 23 chapters, and has 35 patents to his credit. He has successfully guided 65 PhDs and 104 master's students in engineering and technology so far. Sir, I kindly invite you on the dais to grace us with your insightful presentation.
Thank you for your kind introduction, and I'm grateful to the organizers of ChemCon 2023 as well as Mrs. Sinha for inviting me to give this serious, distinguished lecture. We all have been debating, talking about energy transitions, so on and so forth, and all these efforts are especially for attaining what we call as sustainability. We want to have a sustained growth, we want to have a sustained availability of resources, and we want to be in a position to use them in a sustainable manner, not only for our generation, but also for the future generation, which is not yet born. So it is necessary for us to look at these concepts of resource utilization and its optimal utility in a manner consistent with what chemical engineers do in terms of material energy balance and the laws of thermodynamics, which decides some limits. So, the title of the talk which I am going to give today is Progress and Nature. To what extent the progress as we envisage in terms of GDP can be sustained, and how long we can just focus our efforts on ever increasing GDP of the nation, and whether the practices which we are adopting to increase this GDP are sustainable or not. So let me directly launch into the lecture. What we need to consider is the human evolution and its growth. What are the scientific developments which have sustained this human evolution? The industrial innovation, how it has supplemented, complemented the human evolution and growth, which has also resulted into what we now realize certain changes in the climate, and what are the remediation processes which are currently adopted, and how by thinking it holistically we can bring about a paradigm shift in our thinking pattern. If you remember, Einstein had said the problems which we created during the development, the problems cannot be solved with the same level of thinking. We need to have a completely different shift or a paradigm shift in the nature of thinking itself. How long the so-called progress and growth can be continued, and what are the limits to growth, whether it is population or resources, and is there going to be a doomsday? There have been multiple predictions in the past that after this particular year, no oil will be available, no energy will be available, no food will be available, and there will be end of the day, end of the world. This has not happened yet, and we must understand why it has not happened yet. The first prediction was done by Thomas Malthus way back in 18th century, and he said he considered the increase in the resources in a linear fashion and considered the increase in the population in an exponential fashion. And if you consider this, obviously, there is going to come a point where the population will overcome the resources, And that day was considered and predicted as a doomsday. Now, this has not happened. Simple reason being, coupled with the increase in the linear resources of the growth, scientific innovations and scientific inputs has also allowed the scientists, engineers, and practitioners to stay ahead of the exponential growth of the population. And that's why we have now availability of food, availability of health, availability of water resources, so on and so forth. But how long can it really continue? We need to ask that question. If you look at our planet Earth, then it is essentially a living planet, and any living cycle or any living being follows this particular cycle of a lag phase where the growth is slow, followed by an exponential phase which reaches the growth or the population or the increase in consumption exponentially. And when the limits reach, everything gets stagnated, nothing moves ahead, and after some time, the decay starts. If you consider our planet is a living organization, which it is indeed, with all of us on it, it is expected to follow a similar pattern. So the question is, in this exponential growth of a living organism, where we are we at this point? I don't think I'll be able to show it, but essentially it appears that we are in an exponential growth phase. But where exactly in the exponential growth phase? There have been many inputs and many suggestions or many recommendations or many conclusions, but none of them are satisfactory. This was what yesterday, where we were carrying animals, carrying ourselves pulled by animals. Today we are carrying animals pulled by machines. What is going to be tomorrow? And whether technology can sustain and can assist the sustainability. And so far it has, but whether it will continue to do that or not. What we need to look at is the natural capital and how this natural capital is used. Planet Earth is essentially an adiabatic system, completely isolated from the surroundings. This, I think, yeah, completely isolated from the surroundings, no exchange of mass, except probably few meteorites falling on the Earth from the outer space, but that is insignificant. So only input which you get is sun, and this sun energy incident on the Earth manifests itself in the form of different resources, and we'll look into that. So that gives us natural capital, and this natural capital is essentially utilized, exploited for sustaining the economy, for sustaining economic products and services. And this is what we call an ecosystem, and whether this ecosystem is sustainable or not. Availability of ecosystem goods and services, which is natural capital, is essential for sustainability. And this sun energy is the ultimate resource, which is only resource available. So what we use this resource for? It is obviously used for human well-being. And it is three parts. Provisioning, that means we need to provide what is minimum required. Then we regulate it. If we don't allow somebody to hold those resources, then we need to have regulation of those resources. And then there are certain cultural ethics or cultural boundaries which we also need to follow. So it is done for security purposes, whether it is personal security, food security, secure resources, and basic material for good life. The definition of good life also is quite different from culture to culture, from location to location, and we'll talk about that in a minute. Then we obviously want to live a healthy life, so we need to have strength, feeling of well-being, and access to clean air and water, the minimum basic requirements which are there, and good social relationship. Now, all this is going to be dependent on the availability of the resources which are provided by the ecosystem. But what is the status of these resources currently available? Now, if you look at it, There was an assessment which was done by Millennium Ecosystem Assessment where more than 1,300 experts came together. If anybody is interested, they can have a look at this website, which gives the list of the activities which need to be looked at very carefully from a sustainability point of view. This is the condition of our sacred rivers, which you can see to what extent they have been polluted, the quality of the resources which are available, the way we consider resources. We will have to have a different resources later on as a possibility. Waste can be considered as a resource later on. So basically, this is the current condition. Look at the groundwater depletion level. Alarming decrease, especially in the north, which is supposed to be the food bowl of India, Haryana, Punjab, and a quantum of decrease in the groundwater table level it has reached. And this is likely to continue if we do not curtail this huge usage and wastage of natural resources. Soil erosion, again, there are multiple reasons for that. Deforestation is one of the major reasons. So when you see these photos and see this condition of the natural resources, it really makes you worried. At least it makes me worried. And it tends to make me believe that we are sort of tipping the upper part of the exponential curve and we are likely to face the constraints and we are going to limit or reach the so-called stationary phase. These are the conditions of various capitals or resources which are there. The red part is where we have already exceeded in terms of its absorbing capability or assessing capability for our planet. Green part, we are still okay. And the blue part is a place where we need to be careful about. So essentially, you look at biodiversity loss, significant. Because of excessive use of synthetic fertilizers, the nitrogen cycle has been completely disturbed. And climate change, well, there is a debate, but I'll try to prove it otherwise that climate change definitely is there. And there is a thermodynamic reason for it. And I'll explain why this climate change is a real phenomena and not just a phenomena which is to be debated about. This is what tells us. This is the concept of what we call it as an overshoot day or Earth overshoot day. Every country uses the resources which are available, and the only way the resources are going to be renewed in that particular country is dependent on the total solar radiations which they receive during that particular period, let's say 1 year. And out of that renewable part, how much part you are using it this year and how much part of the resources you are borrowing it from the following year. So essentially, when I say that the World Overshoot Day is 282023 from 28/7/2023, that means by 28th of July, world has already utilized resources for the year 2023 and they are borrowing resources from the year 2024. Fortunately, with some awareness which has been brought into the resource utilization in the past 1.5 years with the climate change protocols, COP26, COP28, we have been able to extend this by about 5 days from 28/7/2022 to 2/8. From July, we have gone to August by about 5 days. So if we continue, then this we need to take it to December 31st. Today happens to be December 31st. Before India's so-called developmental cycle in 1992, when the economy opened up, the India's overshoot day used to be in the range of about 24th or 25th of December. That means we were living life in a much more sustainable way. Today, it has again increased to about August or September. That means we are still living in a manner which is not going to be sustainable. Now, sustainability itself is a very funny word because everybody talks about sustainability without actually giving any time frame in it. And we will talk about that particular time frame as well. So this tells us that all those who are relying and exploiting using the resources, you look at all the Middle East countries, the World Overshoot Day or the country's overshoot day happens in January itself. That means for the next 11 months, we are borrowing resources from the upcoming year, coming year, so on and so forth. So every year we spend and submit and use resources by January. You can imagine we are borrowing resources from our future generation. And unfortunately, that future generation does not have any say in it because they are not born yet. They cannot oppose it because we are taking decisions for them, which is not right. So we need to look into ecological footprint and we'll debate and discuss this in a bit more detail. So EFC, I hope the slides are clear to you. EFP, EFI and EFE. So essentially it is related to ecological footprint of anyway, what I am trying to indicate out here is these are the aspects of understanding the impact of any anthropological activity needs to be considered in this particular fashion. How many Earths we would need if the world population decides to live like all those who are living in US? To sustain ourselves, we require 5 Earths. If like in Russia, 3.4 Earths, Germany 2.9 Earths, UK 2.6 Earths, China 2.3 Earths, and India 0.7 Earths. That means 70% of our life is in a sustainable fashion, and we can sustain for a much longer period if we continue to practice the resource utilization which we are currently doing. But if we follow the Western developmental model, you can imagine this earth is not going to be sufficient for us to sustain ourselves. So, coming back to the question of sustainability, what is the period? How long we say that needs to be sustainable? Now, this question will get different answers depending upon to whom you ask this question. If you ask this question to a beggar on the street, he will say, Sir, aaj ka kal ka khana mil gaya to I have sustained myself. I am happy about it. So for him, the sustainability period is 1 or 2 days. For people who are in the middle income, they say, if I am able to generate sufficient to provide my children and maybe one generation further, my grandchildren, I have sustained myself. Rich, of course, they don't have any upper limit. They can keep on using resources. Similarly, if you ask the same questions to people who are in the profession, and you ask that CEO of a company, how long you should sustain yourself, then he said that I have to show profit by next quarter. So my sustainability period is 1 quarter. If you ask a company board, the company board say, my appointment is for a period of 5 years or 3 years. So I need to sustain myself for a period of 3 years. You ask the same question to a politician, they say, till the next election for 5 years. So the definition of sustainability in terms of period will keep on varying, and it is necessary for us to understand that. And if you look at all the dynasties which have existed in India, the longest surviving dynasty was Ahom dynasty in Assam, which survived for 600 years. Now this probably was the reason because of the availability of natural resources in that particular region. They continue to use those particular resources in a sustainable manner, but you will find in majority of the other cases, the kingdom or the dynasty's time period of sustainability varies between 150 to 200 years. So when we are thinking about sustainability, as an engineer, we need to think about 2 generations, at the most 3 generations. That means we need to consider 150 to 200 years as a period of sustainability on the basis of which you will do all the subsequent calculations. So there are external drivers and there are business drivers which ensures the sustainability of an enterprise. Climate change awareness, governmental initiatives, rating and labeling schemes, voluntary codes and standards, which we keep on following without really understanding how and what purposes they are serving towards the sustainability. Environmental advocacy, business drivers such as green and value systems, reputation and branding, shareholders, value creation, competitive pressures, and market opportunities. We keep on doing this, and you know that there are some enterprises in our country which keep on talking about this particular industrial house is known to support the sustainability. For example, Godrej Industries. They will be very conscious of their processes. They will be very conscious in terms of resource utilization, greenery, green belt development, so on and so forth. So this understanding and realization of sustainability in terms of your enterprise is extremely important. Dow Jones Sustainability Indices also indicate regulatory compliance, pollution prevention, product stewardship leading to sustainability. Now, this sustainability is sustainability of an enterprise. And Dow has been in existence for more than 100 years. Godrej has been in existence for more than 100 years. And there are certain organizations in our country which have existed for more than 100 years, clearly indicating that sustainability of an enterprise can be achieved. And this sustainability cannot be achieved unless we are addressing the main issue of sustainability of the society. So we have sustainability strategy, sustainable shareholder value. We have market innovation, which results into resource productivity, profitable reduction in the ecological footprint, reputation of stewardship and social responsibility, market growth. So this is a cycle which continues to contribute to the issue of sustainability of an enterprise. And this keeps on allowing the shareholders to support the enterprise, and if the enterprise is addressing the issues of sustainability, and if the shareholders support this enterprise and don't look at only quarter-wise profitability, then it is possible for the enterprise to sustain itself for a longer period. And in terms of engineering analysis, we need to look at energy efficacy or energy efficiency and eco-efficiency, that is ecological efficiency, how effectively the natural resources are being utilized. Life cycle assessment, byproduct synergy, circular economy, biomimicry, all these aspects are part of the ecological network. Nature is one thing which has survived and sustained itself for so long. There are many things which we can learn from nature. Nature carries out all the conversions, changes without wasting any resource. Can we learn from nature and can we mimic nature? That is what biomimicry is all about. If we can mimic nature, obviously we are addressing the utilization of resources in a more sustainable manner. This is just an example. The analysis which needs to be looked at is not the energy analysis. What is important is the analysis of exergy. Exergy is the usable part of the energy. Imagine if there is no gradient available for you to put that gradient to work, you will not be able to carry out any work. If there is no temperature gradient, you will not be able to carry out any heat transfer. If there is no concentration gradient, you will not be able to transfer any mass. If there is no pressure gradient, you will not be able to move anything. So the gradient which decides the extent of work can be extracted, and that is called as exergy. Just to give you a simple example, let us say I've got huge quantity of water. Let's say that water quantity is in the range of about at 40 degrees centigrade or 45 degrees centigrade. Surrounding temperature is 30 degrees centigrade. So I have a gradient available of 15 degrees centigrade. And huge amount of enthalpy is available. But if the same enthalpy is available to me in the form of a steam, which is at, let's say, 100 bar, then I'll be able to extract much more energy from it. So the quality of energy rather than the quantity of energy is most important. That is what is addressed in exergy analysis. So exergy is energy available for doing useful work, and there are different forms of exergies which are available. This is a definition of exergy. So you have physical exergy, thermal exergy, chemical exergy, where you actually carry out a chemical reaction and extract the energy while carrying out chemical conversions. So energy analysis shows, so the limiting value as far as the sustainability is concerned from a thermodynamics point of view is not energy, it is exergy. So we must look at the destruction of exergy by the use of energy. Say for example, you are using electricity for generation of hot water to take your bath. Energy efficiency is 97, 98%. Yes, but the exergy efficiency is 4 or 5%. The hot water can be generated by using an inexhaustible energy resource such as sun, and that is probably the most sustainable way of producing hot water. Using electricity is a complete destruction of exergy because we are using the highest form of energy, electricity, for carrying out an application which doesn't require that quality of energy. Same is true as far as water is concerned. We treat water to potable standard and use that water in toilets. It is not necessary for us. So to understand the sustainability, we must match the quality of water, quality of energy, and the kind of transformation which we want to carry out. So this is just an analysis which is carried out on the basis of exergy. And this type of analysis allows us to identify a specific operation within your system which contributes maximum to the exergy destruction. And if you can address that, you will convert this particular process, make it more exergy efficient wise. Exergy identifies losses in the equipment and you can act upon those to improve this. So essentially, we need to look at fewer resources, simpler processes, cleaner products, and less of waste. Let me run fast because I don't have much time. Currently, what we are doing is fabrication and package of the product, process and prepare, distribute and support. Our enterprise is limited to that. If we want to recover and recycle, the zone of influence increases. You require much more data for it. And as more and more data comes into play, the system becomes that much more complicated. You want to have flows and impacts in terms of life cycle analysis, flows which are going as an input in services for the final product which you are going to make. This circle, each circle indicates how the complexity of the system goes on increasing. So this is again a life cycle analysis. I'll skip through this very quickly, and mainly because I'm sure at some level during your undergraduate studies, you would have done this life cycle of paper bag or the plastic bag, the kind of analysis which is required, the kind of fuel base, whether it is corn ethanol or gasoline. All these decisions are made by the politicians based on the inputs which are given by people like us. Right? It is not their decision. So while recommending something, it is necessary for us to have a look at these. What it does is resource aggregation. Increase in mass is not necessarily bad, right? But whether it can be used in a sustainable manner or not. Using fuel, which is, let's say, hydrocarbon-based fuel, of course, the energy densities are high. Biomass, energy densities are low. But it has to be used in a larger quantity. And it is always not bad. So we need to analyze everything in terms of exergy destruction rather than anything else. So we need to consider the natural resources and industrial processes. This is what is done. But if you add ecological processes, we need to consider the ecological impact of the industrial processes. And if you consider this, then system becomes much more complicated. And this is essentially called as a system-based approach. And one needs to look at it in that particular fashion. So this is called as cumulative exergy destruction, and this again can be extended to energy systems, soil erosion, stone, non-metallic minerals, natural gas, crude oils. Each of these allows us to assess the sustainability of our operations in our anthropological activities. So characteristics of ecosystems, individual processes are not very efficient. However, every available gradient is exploited to do the work, causing overall system to be highly efficient. Self-reinforcing, resilient network, all this is mainly solar energy, very much in contrast with the industrial system. emulating ecological system may lead to sustainability. Right? However, most methods and disciplines ignore ecosystems. We only look at it our industrial survival or industrial sustainability. So the waste is a new resource. Stop looking at waste as a waste. Waste is a new resource. If you think in terms of future, if you go to Netherlands and if you look at the solid dumping waste sites, depending upon the type of metal, which metal waste, let's say catalytic waste, you are supposed to dump, there are specific sites which have been allotted to you. So if it is nickel containing waste, it is dumped at a specific site. If it is chromium containing waste, dumped at a specific site. This is with an intention that 100 years down the line, 150 years down the line, these dump sites will become as artificial mines in future, so that you will be in a position to use those resources which you have already utilized. So waste is not a waste, it is a next line of resource available to us to address the issue of sustainability. So these are different methods of industrial sustainability assessment, and these methods allow us, and these are the tools which are allowed, which have been used for addressing life cycle analysis, analysis of the ecological footprint of the industrial activities which we carry out. So this is a flow chart explaining approach while calculating ecological footprint, and this is a proposed methodology. I'll give a couple of references at the end. If anybody is interested, they can have a look at it. So this is a system which we are talking about, flow diagram or a methodology to calculate the ecological footprint of your activity. There are going to be waste, there are going to be capacities, there are going to be reciprocal energy densities which are going to be there. You need to consider each and every aspect of it when you are addressing an ecological footprint estimation. One plate of chole bhature, if you consider, it has a water footprint of nearly 400 liters of water. We don't think it that way. But if you look at it right from the harvesting of it, from the cultivation of it, till you actually use it, the quantity of water which has been utilized is significantly high. And one needs to consider all that. Sun is the ultimate source, as we have already said. And what we need to consider is equivalent to, rather than everything used to be done in terms of oil equivalent earlier. Now oil equivalent days are over. We need to consider it in terms of sun equivalent. So, and you will find everywhere that there is 3 to 4 orders of magnitude drop in terms of the quantum of energy which you utilize. Meaning 1 to the power 10 to the power 4 or 10 to the power 5 joules of energy when incident on the earth, about 10 joules of energy which we can utilize at the most. What it indicates that the sun energy, because that is the only lasting energy resource which is available, you cannot really use a platform which itself is not sustainable. So we need to have a platform which is essentially sustainable, and only that is sun energy. So everything needs to be considered in terms of conversion of sun energy to the utilization. So you need to have an energy, and this is called as energy flow diagram, not energy, but energy, there is no spelling mistake in it. Energy, similar to exergy, you have energy, which essentially equivalent amount of sun energy which has been utilized, and that too how efficiently, what is the exergy destruction in it. When I talked about the quality of energy, this is what it is. In terms of calorific value, this twinkle and 2 bananas are same. But can we survive only by eating 2 twinkles a day? 2 bananas will definitely survive us, allow us to survive. So the quality of energy is important for us to understand when you are using that energy to carry out any transformation in a sustainable manner. So look at this. So 10 to the power 6 joules of incident energy results into 10 joules of usable energy. So 5 orders of magnitude in the drop. At the same time, this is also an opportunity. Can we exploit this and improve this energy transformation and utilize sun energy in a much better way? And 1 order of magnitude increase is going to resolve all the problems of the world in terms of energy requirement. One order of magnitude, and it has been achieved in some cases, in some situations. So this is again similar: feedstock, processing energy, product life cycle, and you'll find newsprint, maximum renewability, and quality return on investment. What is important, what you will see in all this, that whenever you use waste as a resource, the return on investment is significantly high. Of course, the capex also increases, but all that needs to be looked in a sustainable manner rather than just 1 quarters or 4 quarters or 1 year horizon. Right, so these are considered as network of industrial systems, and these networks essentially power plant produces SO2, converted to calcium sulfate, water, carbon dioxide emissions. I can use this in terms of concrete block factory. If I want to include the ecological part of it, you'll have forest ecosystem, wetland using the water which is being generated. I can increase it further. So rather than having an only industrial network, we can combine industrial and ecological network. Of course, the system gets much more complicated because we don't have much data for the ecological systems as much. So you can see how the interactions are going to take place, and these interactions will make the system complicated. But engineers, especially chemical engineers, are not afraid of complexity. Right? The more complex situations they encounter, the more innovative they become, and I'm sure by the end of the day, we will be in a position to address the issues of sustainability. Just to sum up, see, there are multiple ways in which the issues can be. So basically, these are the references. So what I'm trying to indicate here is it is important for us to have a socio-economic factors. These are the challenges in network of industrial ecosystem design, carbon tax possibilities, challenges in achieving sustainability. Adopting what the nature does and how the nature does things would be the way forward for us to reach sustainability. Limiting ourselves only GDP and a growth in GDP is never going to allow that, because the thermodynamic law, second law of thermodynamics tells us one story: entropy has to increase, it cannot decrease. The more productivity you have, it means from the disordered resources which we have converted into an ordered product. Now, if we are bringing in order into one, disorder has to increase somewhere else. And this disorder increase manifests itself in the form of increase in the disorder in nature. And that is why we see these floods, we see cyclones, we see droughts, and the intensity of that is significantly increasing. We cannot beat second law of thermodynamics. As long as we are aware of that, I think we will be in a position to address the issues of sustainability, address the issues of progress, and take the demands of nature into consideration. Thank you very much, and I'm sorry for extending the time.
Thank you so much, sir, for your presentation. Now, I would like to invite on the dais Professor IIChE-CHEMCON, Chairman, National Organizing Committee, IIChE-CHEMCON 2023, and Dr. Abhijit Ghosh, Organizing Secretary, IIChE-CHEMCON 2023. And also, I would like to invite on the stage Mr. Pradeep Agarwal, CEO, Heritage Group of Institution, to felicitate Professor A.V. Pandit, sir. Thank you so much, sir. We would request you all to kindly take your seats. Next, we have Heterodrux Professor G.S. Lara ChemCon Distinguished Speaker Award. For this, we are honored to have among us Dr. Shunjit Lahiri, President, Institute Innovation and Incubation Council, NIT Durgapur, Innovation Ambassador, Government of India, and ex-VP Technical HPL. Dr. Shunjit Kumar Lahiri is a seasoned professional chemical engineer with over 25 years of experience in the petrochemical industry across globe. His academic journey includes a bachelor degree from Jadavpur University, a master's degree from IIT Kharagpur, and a PhD from NIT Durgapur. Throughout his career, Mr. Lahiri has held significant role in production, technical services, and technology advisory for esteemed organizations globally. He has he has gotten international exposure through leadership positions in Europe, the US, the Middle East, and Asia, enhancing his understanding of global industry dynamics. He was an ex-vice president technology in Haldia Petrochemical Company. A dedicated researcher, Dr. Lahiri has contributed over 60 technical publications and authored three influential books in the field of chemical engineering. His pioneering work in online fault diagnosis has resulted in European and US patents, earning him recognition in the world for whose contribution to the industry. Currently serving as an associate professor at NIT Durgapur, Dr. Lahiri continues to share his knowledge and mentor the next generation of engineers. His area of expertise includes Industry 4.0 applications, advanced process control, fault diagnosis systems, and energy optimization in process plants. He was awarded Innovation of Ambassador by Government of India. Dr. Lahiri is enthusiastic about contributing to the evolving landscapes of chemical engineering and remains committed to the innovation and academic intelligence. Sir, I would like to invite you on the stage for your presentation.
Thank you. I would like to first thanks the IICHE organizing committee to uh, give me a chance in front of galaxies of chemical engineers here, very big personalities here. I'm very small person among them. So today I will discuss about the futuristic technology where chemical engineering is going. So basically, I will touch upon the AI application to save energy in chemical industries and how AI, artificial intelligence, will affect the chemical industry and where can the biggest impact be expected. So that's the idea. Today I'm going to throw you, and I worked across the world, Fortune 500 companies, and what I find, still maybe we are a little bit delayed in India uh, uh, to accept AI in chemical industry, but chemical industry is going to be driven by AI in very near future. So data is the new oil. So last decade, civilization run by oil and chemical engineers produce oil. Today, British mathematician Clive Humby said, and he rightly said, that data will be the next decade oil, which will drive the industry and drive the civilization. So, how data will affect the chemical industry, that I am going to cover today. So, to give you a background, chemical industry can be divided by four states. It started, say, from mid-century, mid-18th century. Uh, that is called as chemical industry 1.0, and that is featured and characterized by industrialization. So, in chemical industry 1.0, inorganic industry matured, organic industry started. Then we jump to chemical industry 2.0, where the main feature was the scale up. Scale up means very big companies come in Middle East, which really we cannot compete. Other countries cannot compete because of very cheap raw material and very big size of Middle East companies, especially Saudi Arabia, UAE. So nobody else will be able to compete them. So that is a rapid scale up of petroleum industry. Polymer industry started in chemical engineering 2.0, and then chemical engineering 3.0, where there is a significant jump where automation come in chemical industry. So distributed control system and programmable logic control system, DCS and PLC, has come. Computer aided process control system has come in chemical industry 3.0. So every step has a significant jump from the earlier state. And now we are at Industry 4.0, where AI and data analytics will take over. Okay, and the shift is very gradual. You will not see now. Already in foreign countries, it is already felt and seen. But as of now, maybe India it has started. Reliance, big companies has started. But in India, we'll see it maybe 1-2 years down the line. So basically, AI and data analytics and intelligent manufacturing system will be characterized. It is something futuristic. Okay, and sustainability and green plan is the order of the day. So these are the four chemical industries. So we must recognize that we are at industry 4, chemical industry 4.0, and we have to embrace that. And what is happening around the world, slowly there is a transition from conventional to intelligent chemical industry. So what is intelligent chemical industry? Uh, so basically, uh, if we need to understand the big picture of chemical industry, global business is now in the midst of most significant disruption in decades. You know, everywhere we see last year, November, we have ChatGPT, it's changed the world. Okay, and it is going to change the world. And you know, big data, advanced analytics, AI, machine learning, Internet of Things, robotics, artificial intelligence already take over other industries like you know, Amazon. You all know that Facebook, Amazon, all the five biggest industry as of today are using this industry. So this is going to have a very big impact of chemical industry. And why it is on chemical industry? Because there is a one gold mine in chemical industry. Last 20 years, there are softwares available in all big chemical industry where each and every data is get collected. And you know, artificial intelligence is based on data. Okay, if you have a data, those are considered as a gold mine. As I told you, these are the new oil. And chemical industry has last 30 years, 25 to 30 years, all the temperature, pressure, flow, level, and concentrations data are get stored. But the problem is that we have chemical engineers like Honeywell, Aspen, they have developed the software uh, to collect the data and store that data. But the problem here is what to do with that data. That's the problem. And that's what I call data rich and information poor. We have a lot of gold mine, but you have to mine that gold and utilize it. So that where AI will come into picture. So in those data, there are knowledge hidden. So we have to find out what is hidden on those knowledge. And these are very big data. So you know, all over world, chemical industries now emerge as a knowledge-based industry. If you see 10 years before or 15 years before, all the industry which don't have knowledge as their asset, they all wiped out. They get obsolete. Okay. You see our any TV company India has like Onida, you know, they are no more. Okay, so and this is going to happen that whichever company has knowledge as their asset, main asset, they will survive only in near future. Otherwise, within now obsolescence rate are very high. Within 5 years, company will be wiped out. If you see 15 years before, those companies who are giant today they are no more. And today, if you think Zomato, come $1 billion, nobody can expect that such a small idea can change and make a company. Okay, so the definition of a company from raw material to making product is changing. So in today's business scenario, this is the business plan of today, that you have data, you extract knowledge from that data, and once you have knowledge, you take action and convert that knowledge to profit. These are the business plans of today's industry, and chemical industry is not behind that. That whatever data you have, you generate knowledge from that data. They are hidden inside the data, and you generate knowledge and you make profit. Amazon has same business strategy. Facebook has same business strategy. Apple has same business strategy. All the top five companies, they have same business strategy. That you all know that data, knowledge, and then make profit. So chemical industry, how to transform that data to knowledge. As I told you that lot of data are being generated by chemical and oil industry every minute. All companies is generating. It is not only the big companies. As of today, that software is almost installed in all the companies. So this is huge amount of knowledge within this data. And we need to develop advanced data analytics to capture those knowledge and utilize those for profit. Big chemical industries, one thing they are doing, they are hiring data scientists, data technologies to explore the hidden knowledge. And that's where they made a mistake. It is not only a data scientist job, it is require a domain expertise. From data, you will get some insight, but whether those insights has any meaning, that or can we convert that knowledge to profit, that need chemical engineer for chemical industry. Okay, so domain expert is also needed. So one mistake all the big companies like McKinsey, Aspen, they were doing that, they put computer engineer to extract that knowledge. Somehow successful, but without chemical engineering you cannot extract that knowledge. And today, for my young students, I'm telling you, today there is a job called translator. So what this translator do, translator transform that data into business perspective, and they are the highest paid employee in the world. They don't work for a company, they are consultant. They come, spend 5 days, they will tell you, they will talk with the plant production engineers, and they will tell you which data need to be convert to knowledge and convert to profit. That's their specialty. They are chemical engineers. They are chemical engineers with AI, uh, AI knowledge. Okay, so those are called translator. And today, among the world, highest paid chemical engineers are these translators. Okay, they have for 7 days they have a lot of money. Okay, so the next step is use these data analytics to take informed decision in every phase of business. As I told you, generate knowledge from the available data. Manufacturing facilities are transformed from island mode to integrated mode. What it means that you cannot only run your business as a profitable. You have to also consider from where the raw material comes from where full life cycle. Okay, you cannot have a profit only for your business. You have to be a win-win situation. So that is required. And advanced process control and real-time optimizations are there already for big companies. So they were in every minute they were optimizing the chemical plant and reduce the energy, increase the yield. All these things are going on. But today, time has come that among those algorithms, AI will inject AI and machine learning among those algorithms for advanced process control and real-time optimization. And everywhere, knowledge-based decision-making capability has to be installed. So why suddenly there is a surge of this AI? Because of the very simple reason, after the invention of the phone, mobile phone, there is a huge amount of increase of data volume. Okay, and there is a there is a almost 90% reduction of the IoT sensors and cheap computational power. Day by day, with same price, you will get more and more uh, higher efficient CPU. Uh, New data analytics tools are coming. AI, new data analytics tools are coming. Machine learning and artificial intelligence algorithms are coming each year, new and efficient way. And because of this, the value creation from the industry has changed. Changed from say say raw material utilities to data driven analytics. Okay, so let me tell you that how, where exactly this AI and machine learning will impact the chemical industry. So the first one is predictive maintenance. This is, one of the problem of all big chemical companies, that suddenly they have some trip, unplanned shutdown. Suddenly there is a compressor running, and suddenly compressor got tripped, and then you have to stop the whole plant for that, and that is a huge loss. So all the big companies, if you go to the statistics, the 10% profit got eroded because of this unplanned shutdown. Okay, so if you can stop this, if you can predict that shutdown, okay, that there will be an unplanned shutdown, if you can predict by artificial intelligence, by seeing the data, if you can predict, then you don't have to invest anything, you just increase the profit 10%. And 10% means it is in billion dollar, several 100 $200 billion across the industry. So this predictive maintenance means fault diagnosis. This is called fault diagnosis. So artificial intelligence, suppose you have in past, there is a shutdown, unplanned shutdown of a compressor, and you have all the data of that shutdown. And 1 month before that shutdown, how that compressor was giving you indication. Any machine they cannot treat as of now, like human being. Human being, before they die, we always think that, some relative die while you are sleeping. This has never happened. Actually, body gives signal. Always body gives signal. We ignore that signal. We don't know that is a signal. Same thing for machine. Machine always, before a sudden trip, they give signal. Okay, and you have to, artificial intelligence will know that this is the signal. Maybe as a human being, we may not able to tell that this is the signal of a trip. So today there are softwares available made by GE and Aspen, not very effective, but still those softwares are available which can predict the uh, equipment failure. That, say, they will tell you within 2 months this equipment will fail. Second area where this AI will impact is yield, energy, and throughput analytics. As of today, throughout this ChemCon, we have discussed about new technology, sustainable technology, uh, and research. All these are in future. Okay, all these things are in future, and we don't have time. Okay, we cannot have a 20 years, 30 years to do a research and make a viable technology. So what we need to do immediately is apply this AI software, uh, AI and machine learning software, and reduce the energy consumption, increase the throughput, increase the yield. It is absolutely possible. It is going on. Big companies around the world, they were taking this, and then value maximization modeling. It scrutinizes the thousands of parameters and conditions that have impact on total profitability of a integrated supply chain, from raw material purchasing through the complex and often interrelated chemical manufacturing steps to final sales, and then provides intelligence on how best to capitalize at given market condition. Market condition continuously changing. We operate our chemical plant in island mode. We never response with the market condition. Today, suppose petrol price is very high and kerosene price is low. For a refinery, it is obviously for a profitable to increase the petrol price, increase the petrol production and reduce the kerosene production. And then you change the operating condition in such a way. So how to change that? What operating condition I can put so that I can maximize the revenue for a ever-changing international market condition? That's where AI and machine learning will come into picture. Okay, so now I will shift to a little bit one modified area of AI, which is now all the big chemical companies are now developing that. Only one or two is in place as of now, but within 5 years they will flood in chemical industry. Like Reliance make uh, a new department to make digital twin of all their equipments within 5 years. Okay. Similarly, Shell, Dow, they were also doing. So, what is digital twin? Digital twin is a virtual representation of a physical object or system. So, let me tell you, it is a digital counterpart that mirrors the behavior, performance, and condition of a physical machine or process or product in real time. So that is what digital twin is. So this virtual replica is powered by data, advanced AI modeling and simulation, providing a dynamic up-to-date view of the physical world. So you have a reactor, say, running in the plant, and you have a digital twin of that reactor, similar reactor running in your laptop, and they are connected. Whatever going, say, raw material, physical raw material going to the actual reactor, data is going to the digital twin. Same data is going to digital twin, and whatever coming out uh, from the reactor, same thing is coming out from your digital twin. Same data is coming out in digital twin. So what's the benefit of this digital twin? A reactor running in a plant and a reactor running in your computer. So what's the benefit? Benefit is you can change the temperature, pressure, flow, concentration, raw material concentration, anything you can change in your computer and see how it will increase the profit. You can find out that. Okay, so that's the benefit. You cannot always possibilities because chemical plants has a safety concern, and you have always a risk to put it in an actual plant. Okay, so instead of you change the temperature, pressure, flow in actual plant, you change it in your digital mimic plant in your computer and see what will be the effect. And it will give you the optimum condition as of now in real time basis. What should you keep so that you increase the profit or reduce the energy consumption or reduce the emission, reduce the waste generation? All these things, which are the major objective to run a chemical plant, can be done in a digital twin. So the difference between digital twin and simulation is simulation, you just do it for one time. You take the data, you do a simulation, and then it is not connected to the actual plant. Digital twin, on the other hand, is every second it is get connected. Okay, so if in actual plant there is a change, that change will reflect to the digital twin that how this change will impact your product concentration, or product yield or selectivity, you will be able to see. And in actual plant, maybe it will take 1 hour, 2 hour to see the impact of a process parameter. In detail twin, it will take only 1 second. Okay, and you will be able to future predict that uh, what will be the selectivity yield from a reactor or for a distillation column, what will be the steam consumption, energy consumption. So that thing, a digital twin has a advantage. So basically, digital twin has three main area: physical versus digital twin. You know, in chemical plant there are standby pumps, so those are physical twin, standby pumps. But digital twin is, it is a digital replica of your physical system. And then there is a data integration and simulation. So data is going in actual plant, raw material is going, same data is going to a digital twin, and there is a integration and you get the feedback. Suppose sometimes chemical plant has a problem that uh, as of now we don't have so much of knowledge to replicate a complex reaction mechanism. That's a limitation of our knowledge, and that's why it is not possible to make a phenomenological model of some reactor or distillation column always possible. Okay, it is not possible always. So and that's where data-driven AI model come into picture. Hybrid model, say phenomenological model, 50%, 50% data-driven model, and then that will replicate the real plant. And digital twin has a uh, has a feedback mechanism. I will come to that. So, what are the benefits as of now? Digital twin has, it is optimize the plant and improve the process and energy efficiency. My previous speaker always he talked about improving the energy efficiency throughout the ChemCon. You see that energy efficiency improvement is a vital to reduce the emission. So how to increase the energy efficiency in real time? Okay, so that is one of the advantage of digital twin. Second is predictive maintenance. As I told you, it will predict that when equipment is going to fail, and that then you take the maintenance. You know, in chemical plant, the main problem is the big equipment, standalone big equipment like compressors. They were made by, say, Japan. Suppose your compressor failed today or a big turbine failed today, there is no standby compressor. You have to give a order to Japan. The day you order, they will start manufacturing that. Okay, and it will take 1 year, sometimes 6 months, 1 year, 2 years to make that product, and then they will ship 1 month to come here. So throughout this 1.5 year, you have to stop your plant, and that's a huge loss. Okay, so can we predict before it really break down? Can we predict that when it is going to break down, and then beforehand, before it break down, we stop it and then do the proper maintenance? So that is reduced downtime and enhance safety. You know, after this Bhopal incident, this has come into picture that digital twins detect unsafe condition, trigger alerts for immediate intervention, and facilitate safety protocol testing through simulation, ensuring personal safety and regulatory compliance. So all these things are digital twin uh, uh, applications. Now I will show you that how this digital twin in real plant can be implemented. As you see, this part is real plant. It is connected with DCS, distributed control system. So every second scanning time is every second. Every second from plant data is coming, and then DCS take the control action and run the plant. This is as of now, and from DCS, say every minute data is going to a data historian. It is a server where all the data get stored. Now, digital twin application, this is currently, this is there. Now, digital twin application is like this. From that data historian, it will take the data it will go to a separate computer where this digital twin application AI/ML model will be there, and that model uh, will mimic the actual plant. It will predict 24 hours or say 1 week what will be the impact of current condition you have kept, what will be the impact on your profit, on your yield, on your selectivity. It will predict, and then it will not only predict, after prediction it will optimize the process conditions. It will change the temperature pressure within the limit set by the engineers. Within that limit, what is the best process condition which can maximize the profit of the plant, or you can also simulate the digital twin which can minimize the energy consumption or which can minimize the wastage or emission. You can simulate, configure the digital twin in the same way. So this is the digital. So that optimized value, it will give it to a recommendation system to the plant engineer, because this system is not so developed. Technology has not so advanced. So in between there will be an engineer. So it will recommend that to a engineer through a dashboard that what temperature pressure he should keep. As of now, he should change in the plant, and then that recommendation, that plant engineer will ultimately will take the decision, and he will put it into the DCS. So this is what digital twin architecture is there. So it is like this: from plant it is going to a data, and then from DCS it will go to digital twin. Digital twin give the real time recommendation to the plant. Uh, and this is the real architecture, something detailed. Like from data historian, first all the data go to a data cleaning and data validation, because these are data driven model. So if data goes wrong, whole system goes wrong, garbage in, garbage out. So you need a data cleaning and data validation, and then you have a model prediction where AI and ML models are there, and then you have a optimization, then recommendation, go to dashboard. That dashboard give the recommendation to plant engineer, and plant engineer will put back to the DCS. In between, one thing is very uncommon is the feedback mechanism. As you know, whenever in chemical plant, whenever we make some model, it is not that one time you make a model and that model will run accurately for rest of the time. Uh, Chemical plant changes. There are say catalyst deactivates. Okay, so today the very nature heat exchanger have a fouling. So those things you cannot really model very accurately. So this feedback mechanism will tell you that if there is a mismatch between model prediction and the actual plant, because it is connected with the actual plant. So it will take that feedback and it will retune itself, adapt itself, change the model itself to adapt in a new condition, so that throughout its life this model remain valid and accurate. So that is the feedback and auto self training of AI model. So that is required. Okay, so these things I will skip. Uh, so as you know, so this optimization module and this feedback system module makes the digital twin very unique, and that differentiate between a dynamic simulation and a digital twin. Dynamic simulation don't have a feedback mechanism, real-time feedback mechanism. Digital twin have a feedback mechanism. It will adapt itself. Okay, so that it will always able to mimic the real plant. So this auto retailing facility and dashboard and real-time recommendation system. So as of now, this digital twin in chemical industry, digital twin is made in electrical engineering, electronics engineering, but in chemical industry, from 2018, only 10 papers are there. Only 2018, and as of now, only 3 or 4 digital twin which is really implemented in the plant. People are building it, but still not system is not so mature that you can really implement in the plant, because it can put the plant elsewhere if it has a wrong model. Okay, so as of now, we put it from NIT Durgapur, we put it in IOCL Panipat successfully for a reactor, catalytic reactor, and then almost same plant, the biggest plant in the world, we put it in SABIC, one of the SABIC plant. It was running, and from the next day it start giving you the profit. Okay, and it has no cost, almost no cost, just to make that thing. You don't have to. That's the advantage. You don't have to invest anything. Only a laptop. You know, laptop is always available in a. So these are the this auto retailing facility. So let me very quickly go through that how these data analytics methodology very quickly. I will go through. The step one is a data collection. You have to extract the data. This is already available in chemical industry. Second step is data enrichment, where there is a data mining, means which data you have to take as a input, which data as an output, that will come from data mining. Step 3, turning insights into action. That means you put the AI driven tools to support real time decision making and automated uh, execution. Step 4, which is again a managerial decision, is developing a data culture. We take decisions in chemical industry not always backed by data. So now time has come that you always take a decision backed by your data. So digital twin will give you that. And then last point is driving the organization and the governance, and develop the infrastructure, define governance and operating procedures. So uh, these are the main 5 pillars of data driven culture, that is data analytics. In the analytics, you have machine learning, AI, and predictive statistics. Then IT, cloud sourcing, data visualization. Then people, you need mindset change for to implement this. Okay, very old-minded people will not able to implement this. Okay, but there are companies, the leading companies, they already implement it and taking it forward. People and the processes. So this is what, in nutshell, we can do to say. See, reducing energy is not a island mode. It is always connected with so many things. So first is real-time optimization and AI-based APC and real-time optimization, which is already implemented by big companies like Reliance. But now AI will come into picture in their algorithm. Okay, and then implementation of artificial intelligence based online monitoring and energy dashboard, cost dashboard, and waste dashboard. Unless you put it in a dashboard and in front of a operating engineer, you have the data available to top management, that is not sufficient. You have to be in front of an operating engineer, then only he will be able to reduce. So those dashboard, intelligent dashboard, can be made through AI and machine learning. And then fault diagnosis, I already talked. And then online energy loss and energy efficiency monitoring system for every equipment. As of now, we don't have that. For each and every equipment, how much energy uh, efficiency is there, whether it is reducing over time or not, that need to be in front of a operating engineer. And what to do if efficiency reduce, that recommendation also have to come through this AI methodology. And then digital twin to improve yield, selectivity, energy consumption of reactors and distillation columns. And then finally, all the plants. Let me tell you one real thing. All the plant management, they have only and only one objective, and that is to maximize the dollar per hour from their plant. Plant are not running for doing any voluntary things. So profit maximization is the heart of any business. Plants are called SBU. business unit. But this digital twin will maximize the dollar per hour while minimizing the emission and energy consumption. And that's all. Sorry, I could not cope up with the time. Thank you for.
Thank you so much, sir, for your presentation. Now I would like to invite Professor A.S.K. Chairman, National Organizing Committee, IIChE-CHEMCON 2023, to kindly felicitate Dr. Shandin Lahiri, sir. Thank you so much, sir. I request you all to kindly take your seats. Next up, we have the CSIR CSMCRI ChemCon distinguished speaker about lecture. For this, we are honored to have among us Shri Bhaskar Jyoti Mukhan, sir, who is a managing director of Numaligarh Refinery Limited, a leading public sector refinery in the northeast India under Ministry of Petroleum and Natural Gas, Government of India. He is a mechanical engineer with more than 30 years of experience in the oil industry, including logistics, marketing, technical services, and operation. He started his career in Indian Oil Corporation Limited in the year 1990 and thereafter joined Numaligarh Refinery Limited in the year 1999. Prior to his assuming the office of the managing director, he held the position of director of NRL. His leadership has positioned NRL as a key player in India's energy sector, contributing significantly to the nation's energy security and environmental goals through a dynamic hybrid strategy and a clear roadmap towards achieving net zero emission by 2038. Sir, I invite you on the dais for your presentation.
Very good afternoon, distinguished guests, students, ladies and gentlemen. Like my previous speaker, who started off saying that he is matched with some academics luminaries from that field. I am no exception. I am from industry. So my talk, I don't have a presentation, unfortunately, but I will only concentrate on what oil industry has been doing in past decade and what they are going to do in the future decade. Because everywhere you go now, people talk about energy transition. So I thought, because there are a lot of youngsters around, there are very erudite people present in the auditorium. Therefore, I will bifurcate my talk in two parts: what we have done in last decade, and what are the trends that appears to have been emerging at this point when all of us are talking in terms of energy transition. It all started in 2010 when Ministry of Petroleum decided that Indian oil sector refineries in particular has to undergo something called a benchmarking study. So they engaged an internationally renowned consultant who is in the business of only benchmarking in the oil refineries across the world, refineries as well as petchem, of course. So they engaged them and they came up with certain suggestions, and it was found out that all the Indian refiners are extremely poor in terms of energy efficiency. That was a big news for entire industry. It was a wake up call. Second, they hardly know how to maximize profit. So they were thinking that yes, we are making profit because they were mostly in a pricing regime called administered pricing mechanism up to 2000. So it was only a decade old when they actually were exposed to vagaries of the market forces. So they were not looking at profit maximization as one of their major this objective. Therefore, these two twin challenges were to be met in subsequent years. So what did they do? See, this consultant said that there is something called energy intensity index. So it's a complex calculation, and it is their proprietary calculation. So basically, it says that how much energy is consumed by refinery for the given complexity of that refinery. So that is what they calculate, and they normalize it so that apple to apple comparison is possible. So they have a formula for normalizing. See, for Indian industry, they were above say 120, 130 EII. EII, of course, doesn't have a number; it is only an index. And the best of the world used to have EII of around 70. So typically, a refinery of our size, one EII means almost 3000 SRFT. That means 3 TMT of energy we have to gain or spend less to gain 1 point. So as for our refinery, I talk about our refinery. We started from 117 as our EII in 2010. And today, when I speak, it is around 70. So we have come down to how did we do it? So we resorted to all sorts of energy efficiency measure, as was told previously. One is the data driven. We looked at all the equipment individually, the energy consumers, and we prioritize which are the bigger one. Then we attack them first, and we made sure that they only operate in BEPs. Then we focused on reliability, because anytime the things shut down, it is a big drainage. You have to warm up the entire plant. In the plant of our capacity, which is a small 3 million ton refinery, if from shutdown to startup, without producing a single drop of oil, we have to almost consume 300 TMT of fuel just to produce first drop of oil. So that is the magnitude of consumption that you have, which is brought by unreliability. So we focused on unreliability. Another thing that we focused is reduction in steam consumption. Now, how do I reduce steam consumption? We focused on things like stripping steam consumption in the column. So we were actually doing a lot of stripping in the column, which were unnecessary. So we reduced the consumption. We reduced the velocity steam in the vacuum furnaces. So there were a lot of cushions available there. So we started looking at all those things which are readily available for us to reduce. Apart from that, we also looked at better insulation, smarter heat exchangers. We migrated from the normal shell and tube to plate type heat exchangers. We focused on air preheaters, again from the shell and tube to plate type. So we got very good air preheat in CDO, because larger the furnace and the larger the gain. Actually, if you have air preheat coming into that furnace at a higher temperature, then you have a lot of energy saving there. So that is how, in a combination of way, we have reduced the energy consumption from 117 EII to 117. And I mind you, one EII was for 3000 SRFT as a standard refinery fuel. That means 10,000 kilocalorie per kg. So if you translate that, we almost save 200 crore per annum only in case of energy saving, let alone the emissions that we have saved. Second aspect that we focused was something called VEI, Volume Expansion Index. When you refine, actually you want to produce lighter component more, than the heavier component. The heavier is the least price component, because the coke will be the least price, LPG, MS will be high price. So therefore, you want to produce molecules which are lighter density. But within petrol also, if you go and buy petrol in liter. So as a refiner, I would like to, I have a margin of density for MS. Say it starts from typically from 720 and up to 770 I can supply. I would rather supply petrol with 720 density, specific gravity, rather than supplying at 770. So those cushion has to be used up, and those cushions were available inside the plant. Even for designing a new plant, when we came up with plants like DSDT and hydrocracker, you have to be mindful that that you have the option of choosing the pressure at which it will work. Generally, people, it is a trade-off between the hydrogen consumption. Higher the pressure of the DSDT you need, the hydrogen consumption will go up. People typically think that hydrogen is the costliest molecule that you get in a refinery. So therefore, it is to be optimized. The consumption should be optimized. The basic purpose of hydrogen is for stripping of the residual sulfur that you have. You have the sulfur strips in the form of H2S, and the sulfur gets recovered through the closed process. Therefore, people were very conservative about the hydrogen consumption, and initially there was a thought that let us operate the plants at the least possible pressure so that the hydrogen consumption is least. But we were proven wrong. Actually, if you indulge in higher pressure operation, your hydrogen consumption will be higher, and you will get a lesser density product, and you actually end up earning more money. So those were aspects which were not seen earlier, and this benchmarking study had opened our eyes. Now our refineries are much more efficient. We are less addicted to steam. They use the typical term that all Indian refineries are steam addicted. We used to have a lot of steam in the furnace. If you see, there are steam coming for superheating. That all these stuffs were there. The steam pipelines were there. This is why on earth you have a steam pipeline. You put replace the steam pipeline. You put in there's a process fluid pipeline, so that you have a preheat rather than having a higher steam generation. So therefore, but based on the refineries around the world, they do that kind of thing. They are not as steam addicted as Indian refineries are. So therefore, the new refinery which are coming out, a lot of new refineries are coming. We are extremely conscious about our steam consumption. So these are the stories of last decade. That is how the refinery has started looking at one side. They have become extremely energy efficient. Today we are benchmarked quite well, though we have not touched quarter one. Most of the refiners, we are in high quarter 2, but there is a chance to migrate to quarter 1 as well. But it needs investment, and in a running refinery, you can only do so much. Actually, retrofitting is always a challenge in refiners. Second issue is your volume swell kind of a thing, and there is a concept called cost of transportation fuel. People looked at it, and they are earning much better margin than they used to do a decade ago. Now, this is the story of the past. Now, the future that I am talking about, people are talking about the energy transition. Now, energy transition will take which way? Because as has been shown, that concern about the ecology, but ecology, good ecology is also a good economy, because if you emit, you will be penalized in future. And I don't think any bankers are going to fund your project if you are emitting. If you don't have a net zero plan, people will not invest in your shares. So those days are coming. So we are acutely conscious about that. And plans are being made, things are being done. But on the contrary, there is something called energy trilemma. If you happen to visit the BP website, you will see this terminology called energy trilemma. Now, what is energy trilemma? While ecology is to be taken care of, the sustainability is to be taken care of, you will also be very conscious about the cost at which you are supplying fuel, because fuel is needed. Second, the geopolitics is such that you also need a energy security. Not only energy should be available at affordable price, it also has to be available to start with. So these are the trilemma. Actually, one goes, it has to be balanced out. So that means what was seen in Europe, they have cut these two pipelines with Russia, and they started buying everything which is available under the earth, under the sun, including coal. LNG price went through the roof because they stopped natural gas import from Russia, and they bought LNG from all over the world. The poor and developing countries like us suffered a hell of a lot in the last week. That was the cost of living crisis all over the world. So that is what is called energy, the cost of energy. Energy access is something which we all know the geopolitics always influences. As we speak, there are problems in Red Sea, and vessels are coming all across the globe, turning towards the tip of Africa. So those impact our logistical challenge, availability, etc. So therefore, looking at that, energy condition has to be seen holistically. People are charting out different ways of doing it. India, in the context of India, what are the alternatives that are being looked at? One is the biofuel. People are saying that you produce ethanol, blend it with MS. Today we are blending around 13%. It will shortly go to 20%. People are talking of flexi fuel vehicle, which can accommodate around 85% of ethanol in the engine. You go to the petrol pump, you will be saying that you only pour ethanol, I will pour MS separately. So that kind of situation is going to unfold by 2030. This is what one prediction says. But no, from where the ethanol will come? Again, there are two sources. One is from 1G source, that is called typically the biomass, where we talk about either sugarcane or maize. So, but or corn. So these are the typical sources that were being talked about. But last 4 or 5 years, Government of India has promoted this bioethanol coming from lignocellulosic biomass, which are basically waste product. It may be rice straw, wheat straw, cotton waste, or in extreme case like what we are experimenting is trying to make ethanol from bamboo, because a lot of bamboo is available in that part of the country. Therefore, this is one source. Ethanol goes to blended with MS and goes to the old good IC engines. So there, if you go beyond a certain amount of blending, because your oxygenate goes up, you have to modify the engines. Particularly, the metallurgy has to undergo some changes because it will be highly corrosive inside the engine. Therefore, flexi fuel vehicle, which is going to come in future, will have little costlier IC engines, but at the same time, you will be able to swing between the hydrocarbon fuel or the ethanol fuel based on the availability and the price sensitivity of that. This is one area which is being chartered upon. Similarly, diesel is also going to be blended with biodiesel. So it has not caught up that much, but I am sure with the effort of everybody, biodiesel will also catch up gradually. So this is one area people are talking about. EV is a well-known phenomenon, and people are giving emphasis for switching it to EV. There are debates around the corner. People are saying that with the kind of electricity that we have, 50% coming from coal, whether there should be a promotion of EV. EV itself is not very environment friendly when it comes to production of the batteries, because you need cobalt, you need lithium, you need nickel, you need copper in the battery for a motor. Say a typical vehicle will need 38 kg of copper, and you can Google and see from where the prices of copper has gone from 2017 onwards. It has escalated huge in big time. Therefore, this, whether we like it or not, EVs are going to come and stay here. But for that, what India need to do is to upgrade the grid very, very dramatically. The kind of grid support that we have to undergo dramatic improvement to support the EV ecosystem, because EVs are not going to be charged in the petrol pumps or some areas where you can drive in and start charging the EV. Battery swapping is being talked about, but battery swapping, I believe, is only applicable for 2 to 3 wheelers. It cannot go for the four-wheelers, because the battery is huge. Actually, battery constitutes the maximum part of the whole thing. So therefore, battery swapping is not an option for four-wheelers, but definitely it is an option for two or three-wheelers. So the charging has typically to have happen in the residences or the offices where you see the kind of grid connectivity that you have. Definitely, you have to have higher voltage last mile grid connectivity to support quick charging. So that is the need of the hour that needs to be changed before EV becomes very popular and really a sizable number takes over the whole mobility ecosystem. Third area that India is looking at is hydrogen, the green hydrogen business. So green hydrogen actually is something which more of a problem of again electricity. See, to produce 1 kg of green hydrogen, you need 55 kilowatt hour of power. So that is a huge ask. See, suppose government tomorrow says that all these steel plants and all these refineries, they have to use green hydrogen. This mandate is coming actually. In our refinery, we are going to be a 9 million ton refinery, and typically to produce whatever we are producing in form of petrol, diesel, we need 138 kTPA of hydrogen. Roughly, if you calculate, to produce 138 kiloton of hydrogen, you need 900 megawatt of electricity. Now you look at the state of Assam. State of Assam, the peak demand of electricity is 2,300 kilowatt. So in one refinery, in one place, if I need 900 megawatt of electricity, what kind of grid that I have to have? You just imagine. And plus, in India, if you have a grid of 400 kV, you think I have something. This is the biggest. But you go to European countries, their transmission voltage is much higher than 1,000. So India's transmission loss itself is 14,000. So when you are talking of migrating the whole energy chain from molecules to electron, you have to be very acutely conscious, and this is where the investments are going to come. That's why I'm saying that any challenges that I'm tabling today is an opportunity, and people have to work there, and it is going to be worked upon. So therefore, I'm mentioning those challenges. So green hydrogen for industrial use is one thing, and green hydrogen as a mobility solution is another thing. So it is, you must have heard about FCEVs, the fuel cell electric vehicle. That is the way to go forward when you want hydrogen to become a mobility solution, unless somebody solve the puzzle of using hydrogen directly in IC engines. People are trying. Hopefully they are successful. If they are not, then you have a problem in reaching hydrogen as a mobility solution. Why that solution? See, Professor Pandit talked about the energy density. Now, if you look at hydrogen has a fantastic energy density in terms of per kg. But do you know what hydrogen, how heavy the hydrogen is? Hydrogen will weigh less than 100 grams if you take 1 liter of hydrogen. So you have to carry a lot of hydrogen. Now, how do you carry a lot of hydrogen? The only solution is you have to pressurize. People are thinking that I'll put a cylinder and put hydrogen at 700 bar and carry it in the back of the vehicle, and that will supply the required hydrogen to run the fuel cell. And fuel cell, by the way, is not going to come very cheap because they have to have a membrane-like electrolyzer. And today the membrane uses the noble metal and the precious metal. So it has a shelf life. People say that if it runs for 75,000 hours, it is the best. After that, you have to throw it away. But people are working day and night to make these things economical. There will be some back and forth movement. Some technology would seem to be going ahead, moving ahead a little faster than the other. But none of these technologies need to be ignored. So you do not know something will come up and that will make them much more okay. And another area where hydrogen production has a challenge is the availability of water. So you need to split that molecule. You need the water to be in the purest form. See, we in industry use the DM water. That is our holy grail. Actually, DM. Once you have DM water, you only have to strip out oxygen to make it BFW, boiler feed water. That is the best water that we have. But here, in most of the electrolyzer, you have to undertake the process of deionization. Actually, so then only it can be split. But there are again competing technologies. What I am talking about, maybe the alkaline technology. There are PEM and AEM. AEM can tolerate little bit of contaminant in the water. So I don't know which technology will finally sustain. But we are in the crossroads, and these all technologies are competing. If one is more economical, but they need a lot of startup time or something, some disadvantages are there. And mind you, this green hydrogen will only come from green energy. So unless you have a green energy, you cannot have a green hydrogen. This is one challenge. But the government of India's definition is also saying that in a steam methane reformer, if you use CBG, then also you get a green hydrogen. CBG is compressed biogas. That's biomethane. If you use biomethane, then also per definition you will have hydrogen which is coming out of a steam methane reformer. It will also green. But biogas at that quantity is huge challenge. You don't get biogas to that industrial scale. Therefore, these are the challenges and opportunities that will come. Fourth and final thing that I wanted to tell is the opportunity of sustainable aviation fuel. Now, aviation fuel is being made typically by the refiners. That's what we know. But the sustainable aviation fuel, per definition, whatever is known today, has to come from a captured carbon dioxide. You capture carbon dioxide from either flue gas or from the steam methane reforming process, and green hydrogen on the one side. They have to synthesize, make methanol to olefin hydrogenation. Then you get to SAF. Today, SAF is 3 times more costlier than the normal ATF. But there are already mandate available in Western country. Also, India is going to have a mandate for 1% blending. Definitely, SAF is a fuel for future for running aircrafts. So this is one area where enormous work is going to happen in next few years. So I can go on and on the energy transition. Things will pan out. As I have said, some technology will have a head start, but that should not deter the work on the other technology, because these are only beginning to unfold. We don't know which will overtake what at a long point of time. And to cut the long story short, it is too early to write off hydrocarbon as far as Indian contexts are concerned, because for some time we need to use hydrocarbon energy, because our energy basket is not going to change very dramatically so soon. I will just give you one figure. US has a HDI of 0.9, above 0.9, and they consume around, though Professor Pandit has said that now it is not customary to talk about ton of oil equivalent, but being an old timer, I will use the ton of oil equivalent. US use around 6 ton of oil equivalent, maybe marginally more, 6.5 ton of oil equivalent, where their HDI is 0.9. Unfortunately, though we don't like the race to be on the GDP always talking about GDP means consumption, and consumption is not sustainable, but you have to go to a certain level. So our HDI is 0.65, maybe 0.65 kind of a thing. And our TOE, ton of oil equivalent per capita, is 0.6. That means we are 10 times less consuming than US. And our HDI, but definitely whether we consume, not consume, we want our HDI to grow. HDI is a combination of 3 that you know. I am talking to the younger lot, because HDI is combination of 3 parameters: per capita income, the longevity of the people, and to what age you stay put in the education. So these are the parameters based on which HDI is calculated. India's HDI is 0.65. US, where we aspire to go, whether we consume or not consume, HDI should improve. That actually tells about the overall improvement of the community. So they are at 0.9. They are consuming 10 times more energy than us. So even if we don't consume 10 times, whether we will at least we will consume 3 times more than what we do. As we consume 3 times more, you need the entire energy basket. You cannot ignore any energy. You need all sorts of energy, and preferably it should come from renewable. But renewable have these challenges, as I have told. Challenges means opportunity. People should work on that. The energy basket should alter and now tilt towards the sustainable renewable energy. But till that time, hydrocarbon is going to stay. These vehicles are going to stay, and that is the reality. And we, with that, we have to obtain net zero. That is the thing that we are going to see. That means we are talking already about carbon capture, sequestration, and use. So these are the things which are going to happen. And with these few words, because I thought I am little misfit because the erudite academicians are there. I am from the industry. I wanted to give a bird's eye view how a CEO thinks, typically from oil and gas, which is not liked very much by people nowadays. They think that we are the culprit for all the pollutions that we have. So with that, I conclude. Thank you for patience hearing, and thank you for inviting me.
Thank you so much, sir. Now, I would like to invite Mr. Pradeep Agarwal, CEO, Heritage Group of Institution, and Professor M.K. Jha, former IIChE President, to felicitate Sri Bhaskar Jyoti Mukan sir. Thank you so much, sir. Would request you all to kindly take your seats. Moving ahead, we have the Indorama Dhansari, ChemCon distinguished speaker about lecture. We are honored to have among us Sri Vishwanath Chattopadhyay, CEO, IVL Dhansari Petrochemical. He is presently working as a Chief Executive Officer of IVL Dhansari Petrochem Industries Limited, a chemical engineer from Harcourt Butler Technology Institute, Kanpur. Mr. Chattopadhyay has 43 years of professional experience in the polyester industry. He was a core member of project team of Reliance Industries and RIL's first four plants in Patalganga. He has commissioned 11 group projects in India and abroad. His foods are basically detail engineering, construction and commissioning, contracts, etc. Sir, I'd like to invite you on the stage for your presentation.
Good morning and thank you. It's a last minute change as Mr. Suresh Padmanabhan was supposed to give this lecture, but somehow he was stuck up in Indonesia, so he couldn't come. So I'm just a stopgap. Uh, it's not my field, net zero transition, but I thought that I will stick to the theme. I'm from a polymer industry, and I've been in polyester for the last 43 years. But this is a new subject which I just last night I started preparing. But since the theme is with also energy transition, so it will be befitting to close the session or serious session at least with the net zero transition. More than 10,000 years of continuous and accelerating progress have brought human civilization to the point of threatening the very conditions that made this progress possible. And that is the stability of the Earth's climate. The physical manifestations of a changing climate are increasingly visible across the globe, as are their socio-economic impacts. So there are two factors which are continuously changing. One is the manifestations of changing climate, and other is its socio-economic impact. And both will grow exponentially and non-linear way until the world transitions into a net zero economy. Governments, industries, and companies and institutions increasingly recognize that the physical risks associated with a changing climate will continue to build up until the world reduces greenhouse gas emissions and counterbalances any remaining emissions with equivalent removal of GHG from the atmosphere. So don't take the yeah, this one, this one. Same. So to do so will require decarbonizing 6 energy and land use systems such as power, industry, mobility, buildings, agriculture, waste, and restoring the 7th, which is forestry and land use. That acts as both a source of and natural sink of carbon dioxide or other greenhouse gases. So you can see from this slide that the power is mostly generating the carbon dioxide. Carbon dioxide is given in the white circles and the gray circles are of methane. So all carbon dioxide and methane emissions today come from these 7 energy and land use systems. So industry is 50-50. So you can say that carbon dioxide and methanes are produced from the industry. And the mobility, when you are talking about transportation and logistics, it's all carbon dioxide. Buildings are carbon dioxide, but it is much smaller quantity. And agriculture is mostly methane and little bit of carbon dioxide because of the machinery we use for the agriculture. And forestry is also carbon dioxide, but it's a question why carbon dioxide? Because we are losing because of the deforestation, a lot of land is getting exposed. So the carbon content inside the land is giving you the carbon dioxide and the methane generation, and the waste is completely methane. So as of December 2022, more than 70 countries accounting more than 80% of global carbon dioxide emissions and about 90% of global GDP had put net zero commitments in place, as had more than 5,000 companies as part of the United Nations Race to Zero campaign. Achieving net zero would mean a fundamental transformation of the world economy, as it would require significant changes to the 7 energy and land use systems, considering a baseline of net zero as 2050 scenario, when it has been predicted that we should be able to restrict the climate change to 1.5 degrees temperature increase. Capital spending on physical assets for energy and land use systems in net zero transitions between 2022 to 2050 roughly say 30 years, would amount to about $275 trillion. And if I give you the calculator, you will keep calculating how much it will be in the rupees. So in 30 years, we have to, you can see the left side uh, slide that is giving the $275 trillion calculations, and it will require 9.2 trillion US dollar annually for this climate change improvement. Hence, an annual increase of as much as US dollar 3.5 trillion has to be spent for next 30 years, and the spending would be front loaded, rising from 6.8% of the current GDP spending to 8.8% or say 9% till 2026 to 2030 before they start falling. Of course, the technological innovation could reduce capital cost for net zero technologies faster than expected. So you can see from this chart that 2.7 trillion US dollars been spent for high emission assets at the moment. 2 trillion US dollars is been spent for the low emission assets, and 1 trillion US dollars has been spent from high to low emission assets. So there are three segments now in the world, but we want completely spending on low emission assets, so that will require almost 3.5 trillion US dollars per annum. And at the moment, the world GDP is around 105 trillion US dollars, out of which United States is 30 trillion, China is 18 trillion, Japan is 4.5, Germany is 4.25, India is close to 4 million. So you can see now at the moment it has been spent at 6.8% of GDP, but we need to spend 9.2 trillion. For that, it is almost 8.8% of GDP spent is required for the net zero ambitions. The average combined global land and sea surface temperature of this past decade was about 1.1 degrees warmer than pre-industrial temperatures, defined as the period between 1850 to 1900. 1850 to 1900 was the pre-industrial time, which has been decided at the Paris Convention, where they said that that should be the standard taken as 1.5 degrees temperature rise in 100 years. Earth is now warming at the rate of 0.2 degrees centigrade per decade, and losing Arctic Sea, this statistic is enormous, at roughly 3,000 cubic kilometer per decade. That much of ice is lost every year. Climate science tells us that main driver to this temperature increase is the human-caused rise of atmospheric level of carbon dioxide and other gases like methane and nitrous oxide. To stabilize the climate and limit physical risk, climate science tells us that it is necessary to reduce the addition of greenhouse gases to the atmosphere to net zero. As a result of this relationship between cumulative emissions, global temperatures, Earth has so-called carbon budget, a specific amount of carbon dioxide that can be emitted before it becomes probable that warming will exceed a certain level. Intergovernmental Panel on Climate Change estimated that restricting net emissions to 400 to 500 gigatons of carbon dioxide, combined with substantial decreases in emissions of short-lived greenhouse gases like methane, would result in a 50 to 60% probability of limiting warming to 1.5 degree above in pre-industrial levels. So here you can see the corner on the right-hand side. There are four blue circles. The bigger ones, two bigger ones, representing one is India and the other one is China. Since India's GDP is the lowest, almost $2,500 now, so it is on the left top corner. And US having a good GDP and That is why, and the population, these are the circles are basically representing the population. So US at the bottom of right hand corner. So you can, and China is in the middle. So this is the maximum transitional load will come upon India and other developing countries. The vast majority of carbon dioxide emissions, as much as 83%, is energy related. Combustion of coal makes up about 30%, 35% oil, and additional 31%, and gas is around 17% of all carbon dioxide emissions. Here, what are the risks of having this net zero transitions? As high emissions assets are ramped down and low emissions ones ramped up in the transition, the risks include rising energy prices, energy supply volatility, and asset impairment. Around $2.1 trillion worth of assets, power assets alone, that could be stranded by 2050. This is from the McKinsey report. And what are the opportunities? The shift to net zero emissions will create opportunities for businesses and countries. These could be in three areas: decarbonizing processes and products, replacing the high emissions products and processes with low emissions ones, new offerings to aid decarbonization, including supply chain inputs, infrastructure, and support services. So this graph shows that how by 250, these are all idealistic situations. This is because since the targets are two, one is 1.5 degrees Celsius temperature rise, other is by 2050 we have to achieve this. So how to reduce the carbon dioxide emissions? So you can see the segment wise, it is all coming down by 2050, and CO2 removal also taking away, so that the net effect is zero. Similarly for methane emissions on the right side. Energy use accounts for 83% of carbon dioxide emitted across energy and land use systems. Carbon dioxide emissions per fuel and energy and land use systems. This is in 2019 or 2020 chart. The vast majority of carbon dioxide emissions, such as 83%, is energy related. Combustion of coal makes up about 35%. You can see from the chart in the middle, the 35% is from the power. Power is in the black color, and remaining, which is the natural gas, is around 17%, and oil used for 31% for the power. Actions to reach net zero emissions include shifting the energy mix away from fossil fuels and towards zero emissions electricity and other emissions energy carriers, such as hydrogen, adapting industrial and agricultural process, increasing energy efficiency, and managing demand for energy, utilizing the circular economy, consuming power, fewer emissions intensive goods, deploying carbon capture, utilization and storage technology, and enhancing sinks of both long-lived and short-lived greenhouse gases. A key feature of any transition to net zero emissions is universality across energy and land use systems and throughout the global economy. Electric vehicles are valuable only to the extent that low emissions electricity production has been achieved. Reaching net zero emissions will thus require transformation of the global economy. For power, generating electricity and heat through burning coal, natural gas, and to a lesser extent oil accounts for 30% of global carbon dioxide emissions, of which China and USA produce nearly half of that, and 3% of nitrous oxide emissions. Achieving zero emissions, electricity requires accelerating the replacement of fossil fuels in power generation with low emission sources such as wind, hydro, solar, and nuclear. Improvement of storage technologies, use of carbon capture, power to gas to power conversions are some areas where lots of research work is in progress. You have heard over last 3 days, so many speakers deliberated on this issue. And for the industry accounts for about 30% of global carbon dioxide emissions, 33% of methane emissions, and 8% of nitrous oxide. From various industrial processes such as production of steel, cement, chemicals, and extraction of refining of oil, gas, and coal. Decarbonizing industry emissions would require a shift to processes and plants that are more energy efficient, using alternate fuels and inputs such as green hydrogen and scaling carbon capture, utilization, storage for hard to abate emissions, to name a few decarbonization actions. And for the mobility, road, aviation, rail, maritime, and other forms of transportation contribute approximately 19% of global carbon dioxide emissions annually, with USA producing nearly 1/4 of that total and 2% of nitrous oxide emissions. The primary decarbonization lever is replacing internal combustion engines vehicles with battery electric vehicles, and the vehicles powered by hydrogen fuel cells, supported by expansion of corresponding infrastructure, electric charging stations of BEVs and hydrogen fueling stations of FCEVs, plus upstream production of low emission electricity and hydrogen. For the buildings, heating, cooling in buildings contribute about 6% of global carbon dioxide emissions, of which residential buildings account for the majority. Gas or oil boilers with electrical heat pumps, replacing gas stoves and ovens with electric models, and building out infrastructure such as district heating systems that can run on renewable sources and municipal hydrogen works. So these calculations have not factored into the wars. We are seeing now for last 2 years, we have two wars going on. One is Ukraine and another one is now Israel wars. So if you take into account the carbon dioxide produced and used in the ammunitions and other vehicles of the war, so they will be on the fourth factor where there's so much of carbon dioxide is generated if this war also is going on. Now for agriculture, direct on farm energy use and emissions from agriculture practices and fishing are responsible for around 1% of global carbon dioxide emissions and 38% of global methane emissions and 79% of global nitrous oxide emissions. Decarbonizing agriculture would occur through shifting farming practices towards lower emissions practices and technologies, such as making changes in animal feeding, breeding practices, improving fertilization practices, and adapting to zero emissions machinery, and through shifting diets that are currently high in protein from remnant of animals towards one more plant-based foods, reducing food waste by improving supply chains and changing consumer behavior. For the forestry and other land use accounts for nearly 14% of annual carbon dioxide emissions and 5% of global methane emissions and 5% of global nitrous oxide. Forestry contributes to emissions through carbon dioxide released into the atmosphere from land cover change and the release of carbon stored in the soil from land cover change. Currently, 10 million hectares of land are deforested every year. The only way to lessen these effects are to reduce rates of deforestation, replant destroyed forests, and afforest new areas. So for the solid waste, disposal of and treatment, incineration of wastewater treatment contribute to 23% of methane emissions and 3% of nitrous oxide emissions. Actions to reduce waste emissions include diverting more recyclable materials and organic waste from landfills, investing in anaerobic digesters and composters, and implementing on-site methane capture. At present, though, the net zero equation cannot be solved. The greenhouse gas emissions remain high and are not counterbalanced by removals. What's more, the world is not on pace to complete the net zero transition limit and warming to 1.5 degrees centigrade. Based on policies currently enacted into law, the IEA project that warming will be around 2.6 to 2.7 degrees by 2100. Keeping warming to 1.5 degrees will likely require pursuing steep reductions in gross emissions at the same time as investing in carbon capture and negative emission technologies that remove carbon from atmosphere that exist in the atmosphere. This, I think I have already talked about 275. So NGFS, that is the network of green financing services. So they have given a scenario. If we go for a net zero by 2050, then direct and indirect jobs will be created as well as lost. So if you see the middle one, around 202 million jobs, new jobs will be created if we go to this trajectory. However, we will also lose because of the asset impairments, power plants getting shut down, so around 187 million jobs will be lost in the process. So carbon capture, utilization and storage often refers to the engineered removal of carbon dioxide, commonly via amine scrubbing, a chemical process that absorbs carbon dioxide from exhaust gases. Today, around 40 commercial scales of CCS facilities exist globally today, which collectively abate 40 to 50 million tons of carbon dioxide per year. Estimates for the annual abatement level required to achieve 1.5 degree goals range from 5,000 to upward of 10,000 million tons per annum. So more than 100 times current abatement capacity is what is required, and we are at only 40 million tons. The task is humongous. So this is the segment-wise jobs creation, which I just forgot to say. The task is humongous. This shows that the goods traded internationally represent significant cross-border flows of embedded carbon dioxide emissions. You can see the broadest line is connecting the China and US. So it represents the trade volume between the two. Of course, this is going to change because China's economy is going down and other economies like India and Vietnam are going up. So since 2000, the value of intermediate goods traded globally has tripled to more than 10 trillion annually. Increasing production of goods for export trades to increase a country's own carbon emissions, since most manufacturing still involves carbon emitting processes. Here, what is happening, the US is a consumer market, so the requirement of US, which is now getting transferred to the China, and China is manufacturing, so Chinese emissions are going up, but US is not placed in that way. So this way, carbon dioxide emission globally will keep changing between from the time to time, depending upon the trade volumes. Emissions of carbon dioxide and other greenhouse gases have increased from 1970. This is the graph how the carbon dioxide emissions have been growing. At 1970, we had a 20 billion metric tons per year. Now we are at 40 billion metric tons, but you can see a dip there. That dip is because of the COVID, where the industrial activity is going down. These are for the other two gases, methane and nitrous oxide. The top 10 emitters account for 62% of global carbon dioxide emissions and 49% of global methane emissions. So China is sitting at the top with 26% of global carbon dioxide emissions, and after that United States, and India is at number 3 at 6%. But if you see, China and India are comparable because of the population, but United States at 12. So if having 30 crores or 33 crores population, and India is at 140. So there's a 5 times more United States is giving. But however, they are a developed country, but their contributions are not coming through that much. So this is the next slide. This is the percentage of global methane emissions of top 10 emitting countries. China is again at number 1 at 15%, United States at 7%, and India is at 8%. But India's commitment, if not commendable, but it is satisfactory. But the CCPI, that is Climate Change Performance Index, says that India is at number 7 now, and above it is Denmark, Estonia, Philippines, which are very, very small countries. So managing a bigger country is much bigger problem. And 1, 2, 3, you don't see any ranks because none of the countries could satisfy the parameters set by the CCPI. So the task is humongous. We just had the declaration at the COP28 held in Dubai, where all 190 countries have agreed to move away from the fossil fuel by 2050. But challenges remain to effectively store renewable energy, power, alternate energy to drive turbines of the power plant, green hydrogen fuel for mobility, and so on. Entire scientific community are at it and working day and night to resolve this humongous problem. But most important is money. So in 30 years, the world has to spend $275 trillion. And where from the money will come from? 3.5 trillion US dollars excess spending on low emission energy is to be achieved. How to generate this money? Nobody has any idea. Neither COP28 has given any solution. Neither developing countries are also committing so that they will help the developing countries who needs energy to develop their own status. So that is also not forthcoming. So this reminds me of a joke with President Barack Obama. He and his friend, they went to Columbia Business School for MBA, and of course Obama had the political interest, so he came there, and his friend became a good economist, and he wrote a book on how to make money fast. And before he releasing the book, he sent that manuscript to President Obama, and Obama read the book and said that go for the print. The next day, the friend calls to Obama saying that I want to print the book, but I don't have money. Over fact comes the reply from Obama, please read the book. Thank you very much.
Thank you so much, sir. Now I would like to request Professor M.K. Jha, former IICHE president, to kindly felicitate Shri Vishwanath Chattopadhyay, sir. Thank you so much, sir. Would request you all to kindly take your seats. And with this, we come to the conclusion of this session. And I request everyone to please proceed for the lunch. Thank you all. We will resume our session. Good afternoon, everyone. This is your host Shomujit, and I welcome you all to the post-lunch session of IIChE-CHEMCON 2023. To begin with, now I'd like to invite on the dais Professor Anil Kumar Saroha, President of IICHE, Professor A.S.K. Sinha, Chairman of the National Organizing Committee, IIChE-CHEMCON 2023, and also Padma Shri Professor G.D. Yadav Sir on the dais. I would request Professor Anil Kumar Saruha, President IICHE, to read the citation of Dr. H.L.
Good afternoon to all of you. So, I read the citation of Dr. H.L. Roy Memorial Lecture sponsored by Jacob Swarley for ChemCon 2023. The chief architect of chemical engineering education and research in India and the founding father of Indian Institute of Chemical Engineers, in short we call it IICHE, Dr. Hiralal Roy was born on 2nd November 1889. After finishing his school education in erstwhile East Bengal, now Bangladesh, in 1908 with a distinction, Dr. Roy joined the Bengal National College under the National Council of Education (NCE) in Calcutta. In 1910, Dr. H.L. Roy passed the 7th standard examination of NCE, that is National Council of Education in Science, equivalent to LSC, ISC as a topper. The same year, Dr. Roy went to Harvard to study chemistry. He passed the AB examination from Harvard with great distinction in chemistry and returned to India in 1930 to join National Council of Education (NCE) under the Bengal Technical Institute, Calcutta, as a teacher of chemistry. Here, Dr. Roy became keen on introducing chemical engineering as a subject of study. In 1923, he went to Technical University of Berlin, Germany, and in 1925 came back with his doctorate. He joined the Bengal Technical Institute based at Jadavpur University as the head department of chemical engineering. Dr. Roy remained devoted to his alma mater till he retired in 1952. In 1953, he received the distinction of Professor Emeritus. Ever dedicated to the mission of advancement of the chemical engineering education, Dr. Roy founded IICHE in 1947. He became its founder president. In fact, Dr. Roy was elected as the IICHE president for 1948-49 and 1949-50 and later again for the year 1960-61. He was the only president in the annals of IICHE being elected to this post for 3 times. Dr. Roy continued nurturing the institute till he breathed his last on July 26, 1965.
Thank you so much, sir. Now I would request Professor A.S.K. Sinha, Chairman, National Organizing Committee, IICG 2023, to kindly deliver the citation of Padma Shri G.D. Yadav, sir.
Good afternoon. We are into the fourth day, last session of ChemCon 2023. But the activity which we are the speaker Professor of Eminence, ICT Mumbai. Padma Sri Professor Ganpati Yadav is an imposing persona of many a talent who has excelled all the while in his every pursuit. He is a distinguished academic of international repute, an acclaimed inventor, and last but not the least, an excellent administrator, uniquely playing all these roles with ease. Professor Yadav graduated in chemical engineering from the member chemical technology. Presently, he is the Emeritus Professor of Eminence, ICT. He was at Loughborough University of Technology, UK, as a Leverhulme Fellow during 1980-81, and the University of Waterloo, Ontario, as a Natural Sciences and Engineering Research Council Fellow, 1982 to 1986. Professor Yadav is also associated with several universities abroad, including the University of Saskatchewan, Canada, RMIT University, and the University of Newcastle, Australia, and Purdue University, USA. Besides the academic sphere, as a top-notch chemical engineer, Professor Yadav is also closely engaged with a wide range of chemical and allied industries as a consultant and in other capacities. Professor Yadav has made remarkable achievements in fundamental research, especially in the field of catalysis. Along with his research team, Professor Yadav made a major breakthrough in copper chlorine water splitting cycle under a patented ICT-OEC hydrogen production process. He has over 70 patents to his credit. Honors, awards, and accolades have come in his way in abundance. Padma Shri was bestowed upon him in 2016. Best Engineering College Teacher Award of the International Society of Technology in Education in 1994, the IIEE Award of Development of Eco-Friendly Technologies in 1997, Anna University National Award for the Most Outstanding Academic 2005, the Distinguished Alumnus Awards of the UDCT 2006, and Eminent Engineering Award of Institution of Engineers India 2009 are only a few of them. Professor Yadav is a fellow of the premier body of National Academy of Engineering USA. Over the years, IICHE has conferred several prestigious awards upon Professor Yadav. His association with IICHE goes very deep. A life fellow of IICHE, he was its president in 2001 and continues to be one of the most respected vanguards for the institute. Presently, Professor Yadav is a president of Indian Chemical Society as well. In admiration of his many splendid personality, whose achievements have been leaving strong imprints in diverse fields of chemical engineering education, research, and industry, the Indian Institute of Chemical Engineers is honored to invite Padma Shri Professor G.D. Yadav for delivering Dr. H.L. Ray Memorial Lecture sponsored by Jacob Worley on the occasion of ChemCon 2023. Let us give him.
Good afternoon, everybody. I'm indeed delighted to be the last speaker of this conference. Normally, this happens to be the very first lecture because it's a lecture in the name of the founder, Dr. H.L. Roy. And this lecture has a special significance. It so happens that the original awardee, Shri Shrikant Vaidya, the chairman of Indian Oil, could not make it. But at the same time, we cannot have a default. So I was requested yesterday to give a lecture, and I agreed it very happily because I can talk on a variety of subjects. But today, what I'm going to do, because I know this is a afternoon time, people have eaten very nicely during the lunch, so they may have some sort of siesta. They may go into trance, and I will know from here who is going in a trance. So I'm going to see that you don't go into the trance. So I'm going to entertain you. You will enjoy my lecture, and you can search later. You know the things which I'm going to use here. So look at the title. God still is a chemical engineer. That means God was a chemical engineer, and will continue it today. And why did I use this title? Because I had said this several years ago when I was the president of Indian Institute of Chemical Engineers. In 2001, there was a problem because the government announced all these various courses related to, so-called, IT related courses. Everybody, the students started leaving the main courses, including mechanical, civil, chemical. And I was the warden of the hostel, and some students came to me and he said, "Sir, we are going to leave." About 17, 18 of them. I said, "Why?" "I don't think we have any scope in chemical engineering. We'll have scope in IT." So I took them to the mess, gave them nice breakfast, and I said, "I will tell you how chemical engineering is important." But it so happened that particular year, because I was the president, I had to go to many places, and I went to Bhubaneswar. And there was a conference arranged by the local chemical industries, the associations, and you know what they did? They invited the chief secretary of Orissa government for that conference. And the since I was the president, I was the last speaker. Okay, so the chief secretary, in his over enthusiasm, said, "I'm going to close all chemical industry. Bhubaneswar will be Cybereshwar." That's what he said. And the conference was organized by Industries Association, Chemical Industries Association. Now I got up and I said, "Mr. Secretary, I'm going to educate you. If you think that, I can tell you that we don't want any polluting industry, whether it is chemical or otherwise. But you say don't want chemical industry. So I'm telling you that on your body, whatever is there is a producer of chemical industry. And if you don't want chemical industry, you would have to hide your modesty with leaves. Do you want to have it?" And then I said this statement, "God is a chemical engineer." I made this statement, and very next day, the New Indian Express put a headline, "This professor from IIChE-CHEMCON says God is a chemical engineer." Now that became a catchy phrase. You can search it on Google and it is there. So I made God a chemical engineer, remember that. So our students in ICT who had a little low, they printed t-shirts with "God is a chemical engineer." Everybody is wearing that t-shirt and coming to ICT. When I went back, I said students were very happy that. So I said, "Wait a minute. God is a chemical engineer. I said it why? Because chemical engineering is the most versatile discipline. And chemical engineers can do anybody else's job, whether it is physicist, chemist, biologist, mathematician, name it. But other way around, it is not true. And when I said God is a chemical engineer, but chemical engineers are not gods. Otherwise, they will sit in the mandir and the wife has to worship every day. Lighter note, I said it. But now I will prove that why God, I call God as a chemical engineer. So if you do Google search, you will find some videos on me where I have said it is at least it is attributed to me in Google search. Okay. So when you told me yesterday, I said I must prove that God is still a chemical engineer. Therefore, the title. You got the background? The background is that. So why invoke God? You know why invoke God? Why do we invoke God? Oh God, help me. Now, whether it is one God or 100 gods, God means something supernatural power we want to invoke. So maybe we say this. So to help at the time of difficulty, right? So now the word is in the difficulty time. We are talking about nature, we are talking about sustainability, we are talking about decarbonization, name it. Can chemical engineers play a role of a god? And that is what I'm going to tell you. So yes, so we have this peace, prosperity, luxury, and since God is omnipotent, omnipresent, and omniscient, I'm going to show how chemical engineering is like that. Okay, other engineers who are here, there is no disregard, but you want to migrate, change your religion, come to us. Welcome. Okay, so it is all inclusive, all accommodative. That is what the deity does, right? If you don't believe in God, call nature. Okay, I have no issue with that. So this is omnipotent, omnipresent, omniscient. I have deliberately made that Om capital. Now you should know why I made it. Being all powerful, pervasive, and being present all the time in the past, the present, and future, and chemical engineer will be always there. Chemical engineering will be always there. So those of you who want to change your discipline and become some madcap IT guy, who don't do that, I'll tell you how you can enjoy both the worlds. So, and provides material and energy. And what are we doing? We as chemical engineers, we are doing that. We are involved in rate processes. We are involved in waste minimization. We are involved in faster rates, minimum reactor volume, minimum process. So all these things are because of us. So it is Om, right? That omnipotent and all those things. That is the reason I say that. Now, so interesting part is chemical engineering is applied at all scales, from atom to atmosphere. Tell me any field where chemical engineers are not working. Atmospheric cell. Nuclear energy gave maximum number of jobs to chemical engineers. Okay, nuclear. So look at this. Atmospheric, megascopic, mesoscopic, macroscopic, microscopic, nanoatomic. So this is a system engineering approach. That is, materials or energy come through a boundary and only useful energy and useful material will go out. Everything else has to be recycled and reused. And that is what we are talking about, zero waste society. So how chemical engineering will help that? That's what I'm going to tell you. So look at this. You know, I don't know why this Danta Kanti came there, but anyway, I have nothing to do with Danta Kanti, but I'll tell you. CTS, RTS, 40 years. You know what is that? CTS, RTS, 40 years? Does anybody know what is? It should be a dialogue type lecture. Yes, Olympic motto. Okay, this means that faster, higher, and stronger. That is the Olympic motto. Okay, so you look at any of these sports. Okay, any of the sports, everything is possible because of the different kind of materials where you don't have resistance when you go fast. Okay. The material technology has maximum number of chemical engineering applications. Just to change the material and everything else remains the same. So you see that new materials, nutraceuticals, functional foods, all those things. Sometimes the athletes eat some some materials which you don't want them to do that, but that's the fact. So conversion, selectivity, rates, cost, energy, environment, everything is there in that. And that is what we do as chemical engineers. That is what we do. So look at the Olympic records. All these records are broken because of the kind of materials we provide to them. Have you seen the dresses the athletes wear? Have you seen that? It cannot be but for contribution of chemical industry and also this. So this is what it is. You think of any equipment, anything, it is because of this fastest, the lightest material. For example, the bulk density you have to change. You have to change the porosity. You have to change everything. You have to have non-perspiring attire so you can run faster. Because even a fraction of a second can make you win or lose. So that is what was done by chemical engineering. So this is CTS, RTS, 40s, faster, higher, stronger. That is the motto of this Olympic movement. It would not be possible but for contribution of chemical and allied industry. So now this is another poser for you. Can you show any 3 man-made materials or products in this hall, in front of you, or anywhere you think of, which is made without the use of chemicals? Okay. So you will see that there is nothing. If you could get that, name those 3 materials, you will get a prize of 100 million pounds, which is waiting there since 2008. One British gentleman announced this prize. He says, come and take this prize. So I also used to tell my friends in the industry, I will give 100 crore. I don't have 100 rupees of saying that, okay? But I have to say 100 crore because I know it is impossible to find. Not a single product, man-made product, can be made without the use of chemicals. Now the processes should be eco-friendly, pollution-free. That is all part of our business, right? So now here the queen is there. Queen is dead and gone. Now Charles has come over there, but the prize will remain there. Okay, or Charles will go and William will come, right? Something like that is likely to happen. So anyway, and remember, chemical industry is not optional. Because that secretary, Odisha government secretary made that statement because he did not know what he was talking. This is sad. So we have to protect our industry. So this lecture, I said, God is a chemical, 17th February 2001, when I was the president, and this was the headline on 18th February 2001, okay, in the newspapers. And you can see that. Then I also said, but chemical engineers are not gods, so that the housewives, they can little relax, otherwise they will have a problem. And so it is there on the YouTube. Okay, it is there on the YouTube. All right. So then also I gave a lecture later, Home to Genome. And I linked from life to death how chemical engineering has helped us in society. So then I know sometimes you don't know the job of chemical engineering. You might be studying chemical engineering, but what is the definition of chemical engineering? It is true that chemical engineers are compatible with chemistry because most of the time people think chemical engineering means chemistry. Chemical engineering is highly mathematical. Not many people know that. Unless you are strong in mathematics, you cannot do a research in chemical engineering. Okay, the term chemical engineering is not even intended to describe the type of work a chemical engineer does. So it is exclusive. A mechanical engineer will think, electrical engineer, civil engineer will think. But chemical engineering is a different kind of species. Okay, I call it a species, okay? And so look at the scope of chemical engineering. It is an applied science. So we do applied work. It is not just, but we also do fundamental work. Okay? So physical, chemical, and biological rate processes. So remember, we deal with rates. We want to increase the rate of mass transfer, rate of heat transfer, rate of momentum transfer. We want to reduce the volume. We want to reduce the reactor volume. That is what chemical engineers do. So this is where, its applications are going to be helpful in protecting the planet with the principle of sustainable development. Like Almighty God is doing it, chemical engineers have taken upon themselves to protect the planet, and we should do that. Okay? And so see that chemical engineering deals with analysis of rate processes, I mentioned, analysis of systems and system boundaries, deals with space and time, okay, and therefore it is applied from atom to atmosphere, anything you want. And in fact, you saw the other day that Professor Ganpati Ayyappa gave a very beautiful lecture related to biological species, right? And that way he's a chemical engineer. So material and energy with reference to the system. So, so chemical engineering therefore enjoys a special phase in our life, in our society, in our economy. And people should know this. And you are supposed to propagate this message, what I'm telling you. We are accommodative. So I was in UK, Loughborough University, as a Levering fellow. The head of chemical engineering was a chemist, and the head of chemistry was a chemical engineer. At the same time, I'm telling you that, in 1980-81. And so very versatile chemical engineer and plays in the world of atoms to atmosphere, molecules. So the question is that, is there any charm left in chemical engineering, or should leave it and go somewhere else, become IT engineer, right? Something like that. In fact, this is one of the biggest problems we are facing in this country. We are talking about creating $5 trillion economy, right? Then we say we'll go to $9 trillion. Then we say we'll go to $27 trillion. And then we say $30 trillion. Can it be done without manufacturing? Manufacturing is a very important role. Service sector, you can add 70%, but manufacturing 24 to 25%. So chemical engineering, if you don't manufacture, you cannot add to the economy. So this is very important. So then, why should students join chemical engineering? So I will tell you very interesting story about this also, little later. So there are 5 main cycles in life. Okay, we know nitrogen cycle, nitrogen fixation in soil, like carbon fixation in soil. Then we have water, carbon, phosphorus, and sulfur. Now, those of you who understand chemistry, have you heard thiochemistry, the word thiochemistry, where sulfur is there? Life began because of sulfur. Thio is a Latin word that has come from Sanskrit word devas. Devas becomes thio. Sometimes South Indian fellows write TH and D same, right? Vishwanathan or Vishwanathan, right? You know that. The origin is that. That is, it is devas. That is, sulfur is a god. If there was no sulfur, there would not have been life. But these cycles are very important, and because we have disturbed these cycles, we are having problems. Okay, whether it is carbon cycle, it is water cycle, all those cycles. And now the same water is going to come to our rescue in the form of hydrogen, right? So it's very important. So sustainability of materials, energy, environment, and water. So we'll look at this. So these are the so-called 17 sustainable development goals. Okay, look at this. Environment, everybody understands. Climate change, water ecosystem, land ecosystem, how chemical engineering will help in restoration of that. In between, your energy system, industry and infrastructure. On this side, poverty and hunger. We have to have, more food from less land, or tillable land has gone down. So we require fertilizers. Okay, we require all these things. We require pesticides to kill the pests. But we don't want to kill the human beings, but only the pests. So this is, very, very important thing. This is where artificial intelligence, ML, and all those things will come to our rescue. Okay. So listen, this is what the sustainable materials is one, and all these different, goals, like goal 7, 11, 6, 1, 12, they are all shown in these materials. Okay. And we have all these things in this. And at the same time, carbon-free renewable energy. I said yesterday in my lecture, we require energy mix, but no carbon in energy, which is against the policy of the government. Yes, for some time you may have bioethanol or whatever, but in the long run, carbon should not be a part of energy mix, because that is what is emitting carbon dioxide, and we have to bring down the carbon dioxide concentration. This is where once again, chemical engineering will help. This is the World Meteorological Organization. You heard many stories about this, but look at this. Is the 1.5 degree threshold far away? The answer is no. This particular report came on 18th May, It says we will achieve it by 2027. It is bad for us. That means we have to take action yesterday, not even tomorrow. What are you going to do that if you don't, take out carbon dioxide from them? So that is what I'm going to tell you. So look at this particular slide. Just the beginning of the pandemic, the atmospheric carbon dioxide concentration was 410 ppm. During the year, practically we had no economic activity. We know that we were at home, but still we added 2 ppm. And now it is 424 ppm. So carbon dioxide concentration, what they had predicted that annually it should not go beyond 2 ppm. But we have already achieved this. So we are in real danger. So we have to have technologies which will decarbonize the economy, take carbon dioxide out of the atmosphere, and we should not be having carbon dioxide. So otherwise, what will happen? By the year 2050, temperature will grow to something like 8 to 10 degrees, and that will be the end of the world. That will be the end of the world. So we have to protect our future generations. So you see that. So all these things what I reported here, everybody else talks about it, including the economists, including the planners, including the governments. Hydrogen technology, I say carbon dioxide is the new oil because I can convert carbon dioxide into a variety of chemicals and materials. Okay, decarbonization, biomass valorization by 2054, we will not have any crude oil. What are we going to do it? What is going to happen to our refineries? We need a different feedstock. Okay, that is biomass based. Waste plastic recycling. Again, this is related to plastic ban, which is a stupid idea. I'm telling you that. Plastic should not be banned. And I will tell you, instead of that, we should encourage people to recycle plastic. We can use hydrogen to, convert into monomers and other valuable chemicals. So it is upcycling, downcycling, recycling, plastic. Circular economy. And so recycle engineering will be another name of chemical engineers. When you don't have materials, you don't have energy, you have to recycle that. That's what. So this net zero sustainability, chemical engineering has a maximum role to play. So those guys, young guys, remember this what I said. You have a lot of role to play. And again, carbon negative energy systems, we have to develop them carbon negative, not carbon positive. Not even carbon neutral, which is net zero. Net zero is not a solution, I'm telling you that. The entire Western world says 2050, China says 2060, India says 2070. It's a political decision, right? So we have to look at this. So look at the decarbonization sector. People normally talk about transport, but many things like housing, forest, energy, agriculture, forest, land use, all these things require decarbonization. And we have to do that. And look at the carbon dioxide emissions. India is number 4 now in this. If you take the European Union individual nations, then India is number 3. And that is how much is this is the amount 2.622 gigatons, that is billion tons, is emitted by carbon dioxide by India. And so total is something like 36.4 gigatons. Unless we bring down this to 10 gigatons, 1.5 degree will be breached. That means the kind of technologies which we have to develop, and chemical engineers can do it very well, right? So we have to do that. So this is where, because ours is a carbon-based economy, we have landed ourselves in this problem. So on one hand, you have fossil fuels, people talk about crude to chemicals, gas to liquid, okay? On the other hand, we have this renewable resources, biomass, you convert chemically, biologically, thermochemically, whatever, you can convert into a variety of. So we wrote a very interesting paper. This has 10,000 downloads, since we wrote it. And so this talks about many policies across the world. So the use of carbon-based fuels, and this is where you want to take care of greenhouse gas emissions, chemical engineering will come to your rescue. All these processes, very important. So we have refineries, the crude oil refinery, the CO2 goes out, that is greenhouse gas. Another is biorefinery, that is carbon neutral. So what we say plant many, many, many trees so that nature takes care of it. But how many trees you can plant? There is a limit to that. So it is better not to just depend on trees. Trees is very fine, but we have to develop technology to take care of this carbon dioxide. So climate change, net zero is not the solution, but net negative is the solution. And who will work in that area? Chemical engineers will work. Right? That is what I'm trying to do. So again, what is interesting, because chemical engineering is not glamorous, right? It's not sexy. You know? Chemical engineering is not glamorous. So how can industry and academia work together to have mutual benefit and make chemical engineering a glamorous discipline? This is where we talk about institute in industry interaction. And so what, look at this. So chemical engineering will be repackaged as recycle engineering, because we have to recycle everything. Nothing is waste. That is the concept. There is no waste. We convert waste into wealth, whether it is solid, liquid, gas. How many things? And see, remember, we have these solar panels, wind turbines. The year 2000, we introduced them. Their life is over now. They are coming out. What are you going to do that material? Millions of tons of this material. Otherwise, we'll require 3 years in the so-called linear economy. We need to have circular economy. So what is the conversion of waste solids, whether it is biomass, debris, metals, materials, municipal solid waste, industrial waste, we can recycle them, value add to that, valorize. Conversion of liquid, water, solvent, industrial wastewater, sewage, etc. We can convert that. Similarly, gases, CO2, methane, hydrocarbons, carbonyl sulfide, COS, H2S, HCl, SOH, and all of these things can be converted. And believe me, very interestingly, hydrogen comes to our rescue. So I had said that hydrogen is going to be the savior of the world, and this is why I say, because of these many things which we have. So it's all chemical engineering. What I'm telling you, the problems of the world, it's all chemical engineering. So don't sleep. Listen to me very carefully. Okay? So you see that. So I remember, I joke, but I say yes. The Trinity is the Brahma, Vishnu, Mahesh for me is solar energy, wind energy, and hydrogen energy. And I call hydrogen as the prime devas, the first deity. Why? Because hydrogen, wind and solar, except energy, will not give me anything. But hydrogen will give me everything, because hydrogenation of biomass, plastics, and whatnot. So look at this particular. So by this, initially we started with liquids and coal and nuclear. So solid to liquid, liquid to gas. In future, it will be hydrogen is the only fuel, because when we don't have natural gas, what are we going to do? Okay, that is another issue. So you see the hydrogen demand where chemical engineers will work again. So there are many scenarios here. The International Energy Agency, Hydrogen Council, and Transition Commission. See, they predict different things. Somebody said the demand in the net, energy, 73% will be renewable. In that, see, anywhere between 8 to 20.3 or 24% will be hydrogen. And the mixture will be both blue hydrogen and green hydrogen. Blue hydrogen means you have any source, believe me, the hydrogen comes from the water. So if you are doing steam reforming of methane, for instance, or any coal for that matter, you have carbon dioxide is a co-product, you have to take care of it. If you sequester it, CCSU, then, or you use it for something else, then it is blue hydrogen. If it is water splitting, even H2S splitting, there is no carbon, so that becomes green hydrogen. So that is what it is. So we can see that. So if there is a carbon dioxide, because we are worried of greenhouse gas, I can make many chemicals from carbon dioxide, and this is where hydrogen comes to rescue again. So what is my feedstock? Water and air. Because when I talk about, say, green ammonia, it is only nitrogen from air and hydrogen, green hydrogen. So we see we can make many chemicals from carbon dioxide. And same is the case with methanol. Methanol is a fantastic feedstock for industry. Okay, methanol. So in carbon dioxide to methanol, we developed this technology in IICT. We developed hydrogen technology, and I've been claiming that I can produce hydrogen in less than $1, provided I have 100 tons per day capacity. And we are running a plant now in Goa. And so similarly is the case with dimethyl ether. Dimethyl ether is an excellent substitute for diesel and LPG, and the same infrastructure can be used. I can mix DME into LPG. I can mix DME into hydrogen also. I can mix in anything else. And it is also a feedstock. So dimethyl ether. So very interestingly, life itself is controlled by transport and rate processes, biochemical processes, chemical processes. Life is not possible without the applications of chemical engineering principle. Of course, it started earlier, but now we understand. And so human body is the best example of chemical engineering. Thought process itself is a chemical reaction. You know that. When you are angry or when you are calm, these are chemical reactions. So we can understand that. So look at this. So how to make chemical engineering attractive and exciting? One of the things is to having major and minor degree programs. So you can have AI, ML, data science, blockchain in chemical engineering courses. I did it in ICT, I'm telling you. My Bhubaneswar campus has this. I did it because students are attracted, they can make use of it because it is a tool. It cannot substitute manufacturing, right? But it can be used to improve the efficiency of manufacturing. Okay, so that is it. So you see, now who is responsible for declining enrollment in chemical engineering? Number one is parents. Parents are responsible. Number two is media. Number three, image of the industry, polluting. Salary package, most important. If you are giving Dhawal, if you are giving 2 lakh rupees, nobody is going to come to you. You are giving 2 lakh rupees per annum. And there these guys are getting shop floor job, industry rapati. And marriage market, most important is marriage market. In the marriage, if you are a chemical engineer, I said jokingly the other day that there is a, I'll show you this slide here. Okay. So choose the groom from several eligible bachelors. Okay. So parents influence. So I tell you why it is. So suppose you choose a groom from this, and you are waiting in the line, and the girl has to choose the groom. Okay, they will never choose a chemical engineer. We are already married. We are lucky. You know why? Because they think you are the most polluting fellows. Computer wala with high class job, fat salary, but his mobile phone doesn't work without the producer of chemical industry. Right? How many polymers are used? We require gallium arsenide, we require the silicon and whatnot. It is all job, not dirty job is done by us, but the girls want to marry somebody else. What do you do? That is the perception. The perception is created by us. And the media also says, so chemical engineers must have a complete and quantitative understanding of both engineering and science. Because chemical engineering is highly science-based discipline. And this is the first discipline which was transnational. So like suppose I emit carbon dioxide near Pakistan border, it will go there also. Right? It will not stop in our country because it is our pollution. No, that is what is happening. So studies of what we do, applied mathematics, material energy balance, thermodynamics, fluid mechanics, energy and mass transfer, separations, chemical reaction, kinetics, multi-phase reactor design, process design. These are the regular subjects which you study. And they will be there forever, but the applications are at different scale from atom to atmosphere. And to that, these are our foundations, right? Nobody can do research unless you have strong foundation in science subjects. Okay? To that, you can add, to AI, ML data. So chemical engineering is a discipline influencing numerous areas of technology. Okay? Give me any processing industry, name any industry, we will have chemical engineering principles. So I will show you something. And the best chemical engineer is always at home. Mother is the best chemical engineer. Why? Because she knows how to do sieving, chopping, extracting, steam distillation, heat pinching and whatnot. She will put one vessel on the top of another so that heat is not wasted. So mother is the best chemical engineer. Those mothers here, pat your own back because I think you have been teaching this to your kids. All right. So the bread. So you can see the functional materials also when we talk about all these materials is chemical engineering principles. Only then the chemistry might change, right? The scale might change, but it is the same thing which we have been doing. All right. So and the beauty. So most of the time, people who mechanical, civil, electrical engineers they think we do only chemistry. they are in the hallucination. They think chemical engineers means chemistry. Of course, we do chemistry because that is what is our bread and butter. But you don't understand chemistry. What do we do? So here it is. The beauty and charm of chemistry. So the attributes that perhaps most distinguishes chemistry from the rest of the sciences is the ability of chemists to control the structure of matter at the molecular level from complex natural products like vancomycin to nanoparticles and bones units. That is true, but chemical engineers make it happen. Chemical engineers make it happen because they know the tricks of scale up and all. That's what I'm trying to tell you. So, and chemical engineering is a multilingual, entity. Chemical engineers talk many languages, right? So it can talk comfortably with the branches of science, engineering, technology, mathematics, medicine, and technology. Only discipline which can understand and talk something else. I know one professor, Rakesh, what's his last name? He, Carnival, yeah, Agarwal, what Rakesh Agarwal. No, Rakesh Agarwal is in Purdue. There is another Rakesh from Carnegie Mellon. He is now in Harvard. He is a professor. That is also chemical engineering. I am supposed to entertain for 45 minutes. Okay. So you can see that. So chemical engineering in pharma industry, again reactor selectivity, separator, waste minimization, etc. Chemical engineering in polymer industry, same principles we use. Go to chemical engineering in fertilizer industry, use the same thing. Okay. Then dyestuff industry, then in processing, food processing industry, then the oils and fats and waxes industry. You look at the pigment industry. Okay, you look at the solar industry, you name it, whatever you have now, wind energy, chemical engineering, textile industry, chemical engineering, minerals industry, hydro processing is all chemical engineers. Okay, mineral processing, materials industry, coal industry, okay, and you can talk about, is this refinery industry the maximum? So many chemical engineers are employed in refineries. So in other biorefinery now, we are talking about biorefinery. Then we have nuclear industry. Maximum number of chemical engineers were employed by Bhabha Atomic Energy. Many chemical engineers. Okay. So you see that formulation industry. Majority of things are formulation, right? The drugs or paints and all those things. Or biotechnology also. So semiconductor industry. So very interestingly, very recently the Taiwanese guys, what they did, they changed the name of their chemical engineering program to semiconductor. Nothing else is changed. Semiconductor, degree in semiconductor, but what they do is chemical engineering. So you can see that. So same is in the automobile industry. Okay. Then so you look at the versatility of chemical engineering from primary industry to secondary, tertiary, quaternary, and ultimately it ends up as solids. Everywhere it is chemical engineering. Only thing you don't know it, right? Some of you pretend not to know it. So how do you bring respectability to chemical engineering? So who brought respectability to chemical engineering? Bird Stewart Lightfoot. When they wrote that book, highly mathematical, till that time, all other fellows thought chemical engineering means cooking something without understanding the science. But I mentioned to you chemical engineering, highly science-based discipline. So I already told you this. So there are many challenges and many opportunities for chemical engineering, and that is the clean processes, green processes, sustainable processes. Okay, so you can see that we have to expand. And where are you going to expand? And I will tell you some of these examples. They are nanotechnology or downstream chemical industry, whether it is bioprocessing or any maximum chemical engineering principles are used in downstream before it goes to the ATP and whatnot. Okay. So new industries, miniaturization, waste to wealth, circular economy, these are the new industries which chemical engineering will come to rescue. Then what will be the profession 25 years down the line? Okay, we can predict many things, and biotechnology is one area which will not survive without chemical engineering. You have many types of biotechnological processes. So if you want to predict the future, what will be the future of chemical engineering? In one word, it will be most exciting field, because you will understand things not only as a big scale, but molecular scale and atomic scale. You will understand that you have very beautiful models now. So simulation. So like limited access to water will continue to have technology, advancement in purification, desalination, and recycle capabilities. That is going to happen. Membranes will be very hot area, because we want to reduce the energy intensity. New industries will be built on recycle engineering. Okay, recycle. Demand for lighter weight, more durable materials that are fully and easily recyclable will increase, and that is what I told you that Olympic model. Renewable civic infrastructure. Remember, we are building new buildings, old we are throwing. So what are you going to do with that material? You have to recycle it. So recycle engineering. So bridges, roads, electric grids, water systems, and other chemical engineering. So I told you about solar energy, wind energy. So we can have the biopharmaceuticals cannot be done without chemical engineering. That is another area. So this is industry 1 to 4.0. Now people are talking about 4.5 and 5.0 also. So you see that this is all possible. So Internet of Things, big data, and all this. This we have to use with reference to chemical engineering, because these are tools. So we have huge quantity of data collected in the list. So we can see that all those things are there. So for example, this is a chemical factory plant. So we can see we can use AI here. I already told you. So you can have energy system and many things. So this I put a slide here because we are working in this area and we are talking about green hydrogen and carbon dioxide chemicals and materials. So this is my research work in my laboratory. So anyway, so lignin based chemicals, you saw many papers were presented. Lignin is a very good source of chemicals and should not be burned as a fuel. So you can see how many things are possible when you take C5, C6 sugars, cellulose and whatnot. And so we will have many things because it will be word of sensors, and sensors require materials. And who is going to make those materials? Whether it is biological, chemical or whatever. So yes, we will have this. So green energy, okay, renewable energy. These are not just the terminology, but we will expand the limits of the existing carbon-based fuels also. Okay, so you see, this is and I already told you that we have to bring down this carbon emissions to less than 10 gigatons. So transportation fuels to data analytics. Now we are migrating from one to another. So chemical engineering will always remain an exciting field. So ladies and gentlemen, I know you are doing chulbul here and there. So I will go towards the last few slides. Okay. So renewable energy, I told you. Sustainability, I told you. Alternative feedstocks, that is another area where chemical engineering will be very useful. New ways of energy generation, storage and transport, that is another area. Then processing of energy and natural resources, including the radioactive materials. Energy engineering, design of inexpensive, high energy density, quickly rechargeable storage batteries, because somebody talked about batteries. Chemical engineering will come to rescue. Okay. And fuel cells, in fact, another area. Or digital technology, using digital technology, to improve margins. Even if 1% profit is increased, you make millions and billions of dollars. So, ladies and gentlemen, so nuclear power enrichment. So, I have made many slides because I was hoping that my idea of giving this lecture was to get excited and remain glued to chemical engineering. That was the idea. So you can see that new types of information genetics. Okay. Biopharma industry and chemical engineering will be very useful. Okay. Gene editing and chemical engineering concepts. Okay. Or deep learning and chemical engineering. I already told you about this. And process intensification. Okay. Process intensification, chemical engineering, or nanotechnology in space. Okay. On alternate production processes. We Properties of an untreatable disease control and prediction. Chemical engineering will help in this. Chemical engineering will greatly helpful in medical profession. So you can see biotechnology and also gene therapy. So we can do many things. So I'll go towards the end of my lecture. Okay. Risk and hazard management. Chemical engineering is required in this area particularly. And this is the chemical engineering 4.2, where we will have convergence of digital, physical, chemical, and biological things. Okay, that is 4.2. So we have, this is deep learning algorithms and AI. This is a chemical plant. We can increase the profitability. This is a live example from one of the journal papers. So we can see that we can do many things in this. So genomic research, that is disappeared boundaries of biology and chemistry. And so biological engineering and chemical engineering. That is another form of it. Because cells obey the laws of chemistry. Okay? And ultimately, nature is our guide. Therefore, I said God is a chemical engineer, not to, but because we learn many things from nature, right? So nature's chemical factories, you see how many things organisms do. They are chemical factories, so we can learn from them. So from structure to function, that is, we have to meet the biomedical, energy, and environmental needs of the future, and chemical engineering can make it happen. Okay, that is another thing. Okay, and new horizons, generation of semi-synthetic enzymes, ion channels, DNA-directed chemical synthesis, combinator synthesis, construction of biohybrid thin films, enzymes in synthetic organic synthesis, and generation of orthogonal enzyme inhibition. So we can do many. See, this Nobel Prize in Chemistry was given to molecular machines, and that has to be converted into a practice. So yes, so machine learning accelerates catalytic transporting. So that is another thing. Machine learning and catalysis, another area. This Takigawa from Ricardo University gave a very brilliant presentation on that. So I'm going towards the end. So what are the grand challenges? The grand challenges is synthesis and manufacture of new substances by using compact synthetic schemes and processes with high selectivity. Mark the word selectivity, with desired product with minimum energy consumption and benign environmental effect. That is what is required in chemical engineering. You should do that and will do that. Okay? Selectivity engineering, understanding and controlling the reactivity of molecules for all molecular sizes and full range of molecular sizes. New substances, of course, chemical engineers will make it happen. You have to define these new substances. Chemistry of life. If we understand the chemistry of life, we can overcome many diseases. We can find cures for that because it is a host-based relation. So untreatable diseases like Parkinson and cancer and Alzheimer and whatnot. So if you develop medicines based on mathematical models, that will be very helpful. And of course, green chemistry and engineering, everything where we'd like to do this. Okay. So predicting the future of chemical engineering, is it the extension of today's courses? Answer is no. We have to have something else beyond that. So that is chemical engineers. There will be a lot of innovation. To develop solution for some of the today's most important problems like providing food, potable water, goods, and energy to a growing population. All other things are fallout of that. There will be new industries. Consequences of previous and current waste generation will require new industries built around the reuse and recycle of existing landfill materials. Demand for lighter weight, more durable materials, that is going to happen. And so, finally, chemical engineers must aim to address biggest problem facing the society, from atom to atmosphere, solving the mysteries of life, extending the life and making it bearable. It is not just extending the life. Chemical engineering is accommodating and expansion, connecting theory, simulation, experimental analysis, and it should be predictive. And promote openness, reproducibility, okay, and other systems. Okay. So like chemistry has also become, very interdisciplinary. Similarly, chemical engineering will be interdisciplinary, and so it will have the boundaries of science and engineering have already disappeared. It will happen soon. So, chemical engineers' new role will be bringing new technologies to commercial function. Technologies having origins in scientific discovery on atomic and molecular level. Chemical engineers work in molecular world and skill in integrating product design, process control, and optimization, and their skills are needed to develop genetic engineering. Okay. So then only we'll talk about this green economy, bioeconomy, circular economy, and whatnot. And so interestingly, in our human body, biomaterials can replace many malfunctioning parts. 95% of our human body can be replaced by something else, synthetic material, right? And in Bhagavad Gita, we say, Atma and Paramatma, there is a million. Soul goes to the Param, soul, that is God. So that means going from one form to another from body, right? So if you replace 95% of the human body by synthetic materials, biomaterials, you have already done it. They say, na, nainam chandanti vastvani nainam dahati pavaka, na chakledayantyahu, na soshayati manta. So, nothing can dry, nothing can burn the atma, the soul. That is what is going to happen because when we do it, everything. So, final question now: is God a chemical engineer? Because I started with that. Everybody is laughing, but did I not say that? So, yes, who said so? Okay, question yourself if you are awake. Okay, God does. Wait. Okay, thank you very much. And my whole job was to make it a lighter presentation, but you must understand what we are doing in our profession. Thank you very much.
Thank you so much, sir, for such an interesting and insightful presentation, also filled with humor. Now I request Professor Anil Kumar Saruha, President IICHE, and Professor A.S. Kesina, Chairman, National Organizing Committee IICHE-CHEMCON 2023, to felicitate Padma Shri Professor G.D. Yadav. Thank you so much, sir. Would request you all to take your seats. And with this, we come to the conclusion of all the lecture sessions of IICHE-CHEMCON 2023. It was my pleasure to host such a grand conference, hosting such eminent personalities from the field of chemical engineering. With this, I, Shomujit Das, sign off, and now I hand over the podium to Dr. Obijit Ghosh, Organizing Secretary IICHE-CHEMCON 2023, for the valedictory session.
So thank you very much, Somoji. So now we have already reached to our last session, that is the valedictory program, which is most important part of last 4 days event. So I would like to request our today's chief guest, Sri Vikram Sarupji, and LOC chairman, to come on the dais, along with our President, Professor Anil Kumar Sarwaji, NOC Chairman, Professor ASK Sinhaji, Vice President, Professor Rajanandamji, Vice President, Professor Karthikeyanji, and I'd like to request Mr. Vishwanath Chattopadhyay ji and our CEO, Mr. Pradeep Agarwal ji, to come up on the dais. Also, I'd like to request Mr. Sunil Thakurji, President-elect 2024, please come up on the dais. Okay, and sir, the guest of honor of validity program, Professor Jadhav ji, please come up on the dais. Sir, Thakur ji, please. So, a big round of applause for all the dignitaries and particularly for our elected president, Mr. Sunil Thakur ji. So, under his guidance, next 1 year, IIChE will drive. So, I hope that the IIChE will continue its prosperity with its motivation and spirit. So first, I request our today's chief guest, Mr. Vikram Sarojji, to give welcome address.
All distinguished members of IIChE on the dais and off the dais, their families, students, ladies and gentlemen, and also all the delegates who attended this conference. Good afternoon to all of you. First of all, I must thank the Indian Institute of Chemical Engineers to have given us, that means the Heritage Institute of Technology, the opportunity to host this event. This is the flagship event of the Indian Institute of Chemical Engineers, and it's looked forward to the entire year, every year. We started ChemCon 23 on December 27th, 2023. And today we are having the valedictory session on the last day, that's the fourth day of the conference. As in previous years, this year too, we have witnessed lectures by eminent speakers, the Indo-Canadian Symposium, industry sessions, discussing issues related to energy, panel discussions, etc. The theme of this year's ChemCon was energy transition, challenges and opportunities. And it is our Prime Minister's vision and dictate to all of us that India must lead the world in this field. And the Indian Institute of Chemical Engineers will be doing everything in its power to achieve this objective. That means India must lead the field of green energy. Everyone knows that carbon emission is a major problem before civilization today, and we must show COVID-like alacrity to save our dwelling place, planet Earth. There have been discussions on blending of ethanol in regular motor fuel. Plans have been made to extend the use of ethanol in aviation fuel too. In my opinion, Energy mix is a solution for the time being till we can have till we can arrive at a carbon neutral situation. Now, in this case, so we were talking that God must have been a chemical engineer, but I'm sure he must have been all engineers put together. He must have been a person with artificial intelligence. Because even if you have ethanol here, you must have engines to utilize it properly. And for that, you need mechanical engineering. You need instrument engineering for building cars which can use it efficiently. Okay? So I don't agree with Mr. Yadav when he said that God must have been a chemical engineer. Yes, chemical engineer, yes, but all engineers put together. Otherwise, he wouldn't be God. Grant.
All in one.
See, I'm a mechanical engineer, but in ChemCon 2007, where I was also the local organizing committee chairman. At the end of that, I was elected a fellow member of the Indian Institute of Chemical Engineers. At that time, I said, I'm a mechanical engineer, so how can I be made a fellow of the... You realized that all engineering is important. I get much satisfaction in getting to know that students have presented some very good papers. ChemCon provides a learning experience for the students who in a few years will be the engineers working in different plants. I wish them all success. It's also a platform for sharing knowledge, not just learning, but sharing. The people who know have a lot of knowledge, but that knowledge must reach out to everyone. And this is where ChemCon comes in so usefully. The team of Heritage Institute of Technology tried its best to arrange ChemCon professionally, and I'm sure all of you will agree that we did a good job. As LOC chairman, I'm thankful to my team for their sincerity and dedication. I also thank the Indian Institute of Chemical Engineers, the president, the chairman of the National Organizing Committee, the organizing secretary, Shri Vishwanath Chattopadhyay, Shri Pradeep Agrawal, and all my colleagues for doing a wonderful job and supporting me. Thanks to all the sponsors who supported the ChemCon generously. And thank you for coming to Heritage Institute of Technology. I hope that given the opportunity, you will come again and spend time with us. Without all of you participating in this event, the event would not be so successful. Year 2023 is set to become a part of history. I take this opportunity to wish all of you a happy new year 2024. Finally, I wish you all safe journey back home and look forward to ChemCon 2024. Thank you very much.
So thank you very much, sir, for your meticulous planning and guidance throughout the journey. ChemCon at Heritage, under the leadership of our chairman, sir, we work together, and I hope that we are able to reach your expectation. And thank you, sir, once again for helping us. Now, I would request Professor A.S.K. Sinha, who is the National Organizing Committee Chairman. So please, sir. Good evening, all of you. First thing, I should confess that I was suspecting that it will be very thinly attended, but I find that it is best attended session, the valedictory session, and the credit goes to Mr. Abhijit Bose, who is the organizing secretary. Let us give him a big hand for the successful. It is his labor, his hard work that we are seeing that I have no hesitation to say. Of course, you have to judge, but I say that it was a successful 4-day activity. Then I thank the council members who had given me this responsibility and who they had confidence that I will be able to carry out this responsibility, and I had full support from all the council members throughout the year, and I am really thankful to the president, vice president, and all the council members. Then the local organization, I have nothing to say. It is clear to all of you that how much support was from the Heritage Institute of Technology, Sri Vikramji himself and his teammate, including the Agarwalji. I am very thankful to all of you. Then, of course, the volunteers. There were very dedicated volunteers. I could see they were always on time. And some of you can come this side. The volunteers of technical session, I interacted with them, and the other volunteers also. They were very, very, very punctual, very active, very dedicated. I have never seen such volunteers in my life. Then the sponsors also. Without financial support, it was not possible to organize. So my thanks goes to the sponsors also. So coming to the brief, the total registrations were 1,400, much better than what we expected. Industry sponsors were 53. The total number of awards which were presented 55. Lifetime Achievement Award 1, Memorial Lecture Award 4, ChemCon Distinguished Speaker Award 16, Platinum Jubilee Award 4, National Awards 12, Student Awards 14, 18. And list of awardees, prominent among them is none other than Professor Padma Vibhushan Professor M.M. Sharma, Padma Shri Professor G.T. Yadav, Professor A.B. Pandit, Ms. Sukla Mistry, Director Refineries IOCL, Mr. Prabh Das, MD and CEO HMEL, Sri S. Bhartan, Sri S. Bhartan, Director Refineries HPCL, Mr. Arvind Kumar, MD CPCL, Mr. Bhaskar Jyoti Fukan, MD Numaligarh Refinery, Mr. Arup Jhamfri, Opal, Mr. Atul Mulay, Raj Industries, Professor Ganpati Appaiya, IIC's Bangalore, Professor Sanjay Mahajani, IIT Bombay, Professor Ajay Vinu, the University of Newcastle, Australia, Mr. Alok Sharma, Executive Director CHT. So this in Chemical 2023, the council had decided that the speakers will be a mix from industry as well as from academia, so that there is a greater interaction between academia and industry. And we have successfully followed the instruction of the council. There were oral and poster presentation. Total number was 825. There were 7 themes, including transformation, energy transition, and energy environment. There were invited lectures also, 28. Number of technical sessions were 56, which includes 2 online sessions. Total number of oral presentations 632, massive 632 oral presentations in the parallel session. Total number of poster presentations 161. So on all account, I will say that it is the hard work of Vijit and his team. What we could see that there was a massive participation throughout the country and also from the abroad. So now this time also council wanted that we should have a panel discussion. So we had 3 panel discussions also. One was an affordable and sustainable energy mix for India's energy transition. Second was readiness of chemical process industries towards net zero with COP28 mandate of suitable action. And the third, which was chaired by Professor M.M. Sharma, and panel member was Professor G.D. Yadav, and I was also a member. The role of IICHE in promoting industry-academia interaction. It was there were certain suggestion that IICHE council members are should see that this interaction is improved. We have the aspiration, we have the desire that IICHE should provide a platform for better industry academia relationship, modality, etc. IICHE can themselves decide. The other event includes submission of Summit of Indian Chamber of Commerce, and there was also Indo-Canadian Joint Symposium. 14 papers, 7 from Canada and 7 from India were presented. Then we had MOU signing between IICHE and European Federation of Chemical Engineering, and between IICHE and AICHE. So there were so many activities going very smoothly, and there was therefore we could not have the feeling that we have conducted so many activities in 4 days. And again, I will appreciate the effort of Mr. Abhijit Bose and his teammates. Now, I have briefly written some summary of the presentations and deliberations which were made. I will read that out. It is first draft, or let us say it is 0th draft. I will refine it and submit to the council member. Council. India economy will expand to $5 trillion by 2025 and $10 trillion by 2030 from current $3 trillion. Its share in global energy demand is expected to double from its current 6% to 12% by 2050. It is already the 4th largest energy consumer, with primary energy consumption doubling in the last 2 decades, and is poised to become the 3rd largest consumer by 2030. Over 80% of energy needs is met by 3 fuels: coal, oil, and solid biomass. Coal accounts for 44% and oil makes up for a quarter. The share of natural gas is 6%. Currently, 85% of oil and 50% of natural gas are imported. The share of natural gas will increase from 6% to 15% by 2030. Carbon dioxide emission in India remains low by international standards, but 14% of global energy sector emissions growth since 1990 has nonetheless come from India. The carbon intensity of India's power sector is 725 gram of carbon dioxide per kilowatt hour, compared with a global average of only 510 gram carbon dioxide per kilowatt hour, underlining the predominant role of inefficient coal-fired generation. India is the 3rd largest global emitter of CO2 despite low per capita CO2 emission. The carbon intensity of its power sector is well above the global average. The share of coal in the energy mix has not really changed since 2015. The tremendous growth of renewables has tempered growth of coal capacity but not prevented it. India's future prosperity will hinge on affordable, clean, and renewable energy, and the scope of further growth in energy demand and infrastructure is huge. Solar power is set for explosive growth in India, matching coal's share in Indian power generation mix within 2 decades. Today's clean energy momentum enables India to outperform its Paris pledge. The energy sector landscape in India has witnessed tremendous changes. Policy has focused on an accelerated and ambitious plan to increase the contribution of alternative source of energy such as renewables, green hydrogen, biomass, ethanol blending, CCUS, etc. It is of strategic importance for India, which will be one of the world's largest market for these technologies in the decades to come. India needs to position itself at the technology frontier to maximize the benefit of energy transition. It should be to be a technology maker, not a technology taker. There are few clean technologies which have dominated the energy transition so far, namely solar photovoltaic, wind, and lithium ion batteries. But there are certain limitations to this. There are cost, technology, and particularly barrier to full scale electrification of all existing energy uses, which limits the extent to which renewable electricity can directly replace fossil fuel. Liquid fuels derived from crude oil have a high gravimetric energy density. This explains their widespread use in the transportation sector, which accounts for around 60% of global oil demand today. A liter of gasoline weighing around 0.75 kg contains around 35 kg of energy, whereas a lithium ion battery today can store the same quantity of energy when fully charged but would weigh around 50 kg. This weight constraint can be offset to a large degree by increased efficiency of electric motor to 2.5 to 5 times more efficient than internal combustion engine, meaning the effective battery weight requirement of electrical vehicle can be reduced accordingly to a given driving range. Nevertheless, the disparity in weight helps to explain the difficulty of directly electrifying long distance transport modes where the weight of the fuel is a critical parameter. This is particularly the case in aviation, where the gap between the efficiency of electric motor and jet turbines is small, and where regenerative braking cannot compensate for the added weight of the batteries. In industry also, the full-scale electrification of the process heat will involve high cost and technical, technically challenging. So, what is uh, the future strategy that India must ensure that the energy transition does not result into foreclosing its development option. Community-based adaptation forms an important part of energy transition. Coal will remain in the short to medium term. Process such as supercritical technology with higher efficiency and CCUS should be adopted. Gas will be a bridging fuel. Hydropower can play a role. Building up and import of hydropower from Nepal and Bhutan is a long-term solution also. Electricity would be the dominant part of overall energy system with a smaller contribution coming from bioenergy. A significant part of electricity would be consumed for production of hydrogen to be used in industry and transportation. It is likely that hydrogen will be produced directly leveraging heat from solar and nuclear energy. The land requirement must be considered in making energy mix choices for net zero emission by 2070. The fundamental benefit of biofuels is that they may provide a low carbon alternative to fossil fuel based liquid transportation fuels such as gasoline, diesel, and aviation fuels, while also assisting in reduction of carbon emission. As a dense source of energy, nuclear power can play a role in producing hydrogen through electrolysis as well as through thermochemical splitting of water. India should focus on R&D and technology development to be on the global frontier in each part of the value chain of green hydrogen with the objective of lowering cost and increasing deployment. This requires a coordinated push. The supply side also with increased investment and R&D commitments, as well as the demand side support. Electrolysis alone will not be sufficient to generate all the hydrogen predicted to be needed for future demands. Exploitation of solar radiation in the form of heat or in photocatalysis holds considerable promise. Photoelectrochemical catalysts with the ability to produce hydrogen under visible light irradiation are currently under research and development to enhance their durability and efficiency and cost of materials. Biological routes for hydrogen are under development and set to impact the hydrogen energy sector. Biomass is set to make significant impact through gasification, pyrolysis, and fermentation. Current technology that produces alcohol, mainly ethanol, by fermentation could also be seen as a route to hydrogen by electroreforming. Overall, there are a significant number of options and technologies for hydrogen production that are potentially sustainable and avoid the use of fossil fuel. Ammonia is considered a potential storage compound for hydrogen because of its known chemistry of formation from hydrogen and nitrogen. Hydrocarbon-based compounds, example methanol, octane, benzyl and dibenzyl toluene derivatives are both liquid and high-density hydrogen storage compounds and high-yielding density fuels. Carbon capture, utilization and storage will need to form a key pillar of efforts to put the world on the path of net zero emission. Stronger investment incentives and climate targets are building new momentum for CCUS. CCUS can be retrofitted to existing power and industrial plants. CCUS is virtually the only technology solution for deep emissions reduction from cement production and the most cost-effective approach in many regions to curb iron, steel, and chemical manufacturing. Sustainable aviation fuel from captured CO2 and hydrogen is the one of the limited number of low carbon options for long distance transport, particularly aviation. For emissions that cannot be avoided or reduced directly, CCUS underpins an important technological approach for removing carbon and delivering a net zero system. So a major ramp up of CCUS's deployment is required in the next decade to put the global energy system on track for net zero emission. Government has a critical role to play through policies that establish a sustainable and viable market for CCUS. No sector will be unaffected by clean energy transition, and for the same, including heavy industry, the value of CCUS is inescapable. We will have to boost innovation to reduce cost and ensure that critical emerging technologies become commercial, including in sectors where emissions are hard to abate and for carbon removal. New pathways involve transforming CO2 into fuels, chemicals, building materials. These chemicals and biological conversion processes are attracting increasing interest from government, industry, and investors, but most are still in their infancy and face commercial and regulatory challenges. The production of CO2-based fuels and chemicals is energy intensive and requires large amount of hydrogen. The carbon in CO2 enables the conversion of hydrogen into a fuel that is easier to handle and use. For example, an aviation fuel. CO2 can also replace fossil fuels as raw materials in chemicals and polymers. Less energy intensive pathways include reacting CO2 with minerals of waste streams such as iron slag to form carbonates for building materials. We should understand that CO2 used is not the same as CO2 avoided. CO2 use does not necessarily reduce emission, and quantifying climate benefits is complex, requiring a comprehensive life cycle assessment as well as understanding of market dynamics. CO2 use can provide climate benefits where the application is scalable, uses low carbon energy, and displaces a product with higher life cycle emissions. Long term, in the longer term, a net zero CO2 emission energy system, the CO2 would have to be sourced from biomass or the air in to achieve climate benefits. CO2 derived products that involve permanent carbon retention, such as building materials, can offer larger emission reductions than products that ultimately release CO2 to the atmosphere, such as fuels and chemicals. CO2 use is not expected to deliver emissions reduction on the same scale as capture and storage, but can play a role in meeting climate goals as part of all technological approaches. If not being used on site, the captured CO2 is compressed and transported by pipeline, ship, rail, or truck to be used in a range of applications or injected into deep geological formations, including depleted oil and gas reservoirs or saline formation, which trap CO2 for permanent storage. These technology-based approaches for carbon removal can be complemented and supplemented nature-based solutions such as afforestation and reforestation. So this was my first draft. I will refine it again. I had a difficult time, and the culprit is Abhijit Ghosh only, because he had so much activity in 4 days that it was difficult to have the draft prepared. So thanks to Abhijit Ghosh. He made my life difficult in the 4 days. Thank you again, and happy New Year. Wish you happy New Year, and hope to meet. Not hope to meet. I am sorry that we'll meet in ChemCon 2024 in Jalandhar. Thank you very much.
Sir, thank you, sir, for giving all your summary and guiding us all these last 2 years. Whenever ChemCon discussion required, I used to call sir, and with the help of MS Bala sir, he was working with me every day and night. So we are talking each other. So thank you for support from the IIChE-CHEMCON sir. So now I would request Professor G.D. Jadhav sir, guest of honor today valedictory program, to address the audience.
Sri Vikram Swarup, Chairman of the LOC, Professor Saroha, the President of IIChE, Professor Sinha, Chairman of LOC, the newly elected President, Mr. Sunil Thakkar, Pradeep Agarwal ji, Vishwanath Chattopadhyay, Chatterjee or Chattopadhyay? What is right? Swadan Chat, okay. Vishwa Chat. And then Rajanandan ji, Karthikeyan ji. And in the audience, we have many stalwarts here, including our friend Basav Chowdhury. Yeah, you are just sitting behind the thing, but you are doing everything. Thank you very much. And all our distinguished council members and others from the Calcutta Regional Center, delegates, the wives of council members, they were very important part of this. And I should not forget Baba. Okay? Baba was very important. Ladies and gentlemen, you already heard me. So once again, I don't want to extend that, but only one thing I want to say is that it was a fantastic ChemCon 2020. Give a big round of applause for all the organizers. And I know how hard it was for Abhijit. Abhijit is working with me in another capacity. I won't reveal that, but Abhijit was working very hard and he was really worried person. So Abhijit, you can go and relax now. Okay, don't have to worry. Basab will give you leave for a couple of days. Huh? And of course, you did not see which I noticed. Pradeep Agarwalji was everywhere. So your support was the most important support for ChemCon. You did wonderful. See, sometimes when things happen beyond expect, you go to win a match and you got gold medal, right? And so we had a gold medal here because ChemCon 23 was excellent program. In terms of monetary support by various organizations, including our Reliance Industries, we have been supporting since 2004. Every year they give 25 lakh. And of course, in Mumbai, they give more, and we will expect more from them in the future. But most important part is the participation by delegates. 1,400 abstracts is I think, a record of all sorts. It's a record. So we congratulate you. I hope the delegates are here because we are going to distribute some awards. Are there presentation awards? Except me, right? Okay. All right. So good that everybody is there, and so they will receive their awards. And when you go home, you should enjoy and participate next year also. Next year it will be in Jalandhar. Where is the Jalandhar man? Ajay Bansal and MK Jha. Where is the, oh, he's there. Okay. Next year, you are not coming and telling something about your. Okay, you are going to come and tell us. Okay, very good. So, ladies and gentlemen, I want to compliment all of them who were involved in organizing this. I don't know when I was sitting in the audience and on the stage. Right? Every now and then I was called. I used to think I will relax, but it don't happen. But good. So, in sum and substance, ChemCon was a huge success, and I want to thank each and everybody. And one of the persons who was working very hard during this is Professor Bala from IIChE-CHEMCON. Give him a big hand. Bala is there. The poor fellow was looking after the ChemCon Distinguished Speaker Award, their citations, their printing and all. And also he was looking at Professor Sinha, whether he has made him happy or not. But Bala, at least you have made all of us happy. So we gave him a big round of applause. And of course, all others. It was a wonderful program, I must tell you that. And so I hope you will continue to shower. No, of course to you. I should not forget RGIPT Director Professor ASK Sinha. Give him a much bigger round of applause. I was going to say at the last, but since you reminded me. And of course, Saroji, calm and quiet, as if nothing is happening in this world. Very calm and quiet president. Very calm. And we are having incoming president, Sri Sunil Thakkar. So we expect more than this next year, right, in Jalandhar. That is not your part of Gujarat, but it is in Punjab. So we have to go to Punjab and see that we do a good job. Okay? Very good, very good. So it is already started. So ladies and gentlemen, I once again thank all of you for coming over here. I have been part of IIChE ever since I returned to India in 1987. Except 3 ChemCons, I have attended all of them since then. All of them. So I know what is happening. So thank you very much for asking me to be the chief guest of honor. Thank you so much, Abhijit. And you have done a wonderful job. I will pat on the back. Well done. Thank you.
Thank you very much, sir. So now I request our Vice President, sir, Professor Rajanandan ji, to say a few words.
Respected dignitaries on the dais, of the dais, and my dear friends, delegates. So very good afternoon to all of you. So now, like a dream, so this 4 days extravaganza is just coming to an end. In fact, we have revealed very well, and I think much of the credit, apart from the organizers and the management of HIT, it also goes to the donors and the sponsors. In Sanskrit, they say, Agata Vamsadoshaya Karma Doshe Daritata. That means if somebody is not a giver, if not, somebody is not able to give or not a donor, I think there is a problem with their hierarchy. And if somebody is not, somebody is simply idle, then it leads to poverty. So that means the people who are giving, they are really, I think we have the hats off to their hierarchy, their dynasty, their parampara. They are Datas. And I am surprised really when I heard so Professor M. Sharma 2 days back when he was telling that in 1975 itself, so our Dhirubhai Ambani ji has donated 1 crore rupees to UDCT. Sir, 95, sir. 95. So that is a great thing. But apart from that, I really appreciate the management of the Heritage Institute of Technology and particularly the work done by the Secretary Avijit. He is everywhere. I'm really surprised on the first day when we had taken a photograph with the governor, the next day it came in a sort of big pamphlet and such is the fastness and really Avijit, so nice of you, so good of you. So in fact, really, he's an asset. He's an asset to this SIT, and really, the SIT is fortunate to have the faculty member who is highly committed like this. I think most of the faculty members are like that. Now, apart from this, so this HIT is having certain records also, as far as the ChemCon is concerned. And Professor G.D. Yadav has already said that this is a fantastic ChemCon. See, last year they have conducted the IIChE-CHEMCON and this year they have conducted the ChemCon 2023. I think this is a record. No institute, as far as I know, did not conduct in consecutive years both IIChE-CHEMCON and the ChemCon. That's a record. Maybe ACM. Yeah, I saw. Okay. Yes, that is one. And second thing is, so the number of this one, the boards and all. So they are. I have not seen. I have attended several ChemCons. I have not seen so many boards everywhere. So much of say the decoration and all. It is also very nice. And one more record is there. That also, if it is wrong, you may correct. Dr. Abhijit is the organizing secretary, not organizing secretary, sorry, honorary secretary for the organizing secretary for IIChE for 4 consecutive years. So that is also a record. I think that record will not be broken at all because so normally the council time is only 3 years. Okay, so it so happened in his case only he is 4 years. So with this, really it's a great, I'm very, very happy to just participate in this ChemCon.
Yes, yes.
And caterers and also the transport and accommodation. I've heard. The transport and accommodation are very good. Whenever we just call, so Rahmanji, so he immediately sends a vehicle. So the transportation and accommodation, then so you take any aspect, everything is very nice and fantastically arranged, and also the infrastructure here is also everywhere. We have a very good infrastructure in HID, and for creating such a good infrastructure, I uh, okay, I appreciate the management for their commitment. Thank you.
So thank you very much. So now I request Professor C. Karthikeyan, Vice President IIChE, to address the audience.
Most respected dignitaries on the dais and off the dais, my dear young student friends, good evening. It gives me immense pleasure to participate in this valedictory function of ChemCon 2023. There is a saying, full many the gem of purest rays born in unfathom cavern of ocean, and full many the flower of sweetest fragrance born in a desert is a waste. Let me slowly tell. Full many the gem of purest rays. Full many the gem of purest rays born in unfathom cavern of ocean. Nobody knows how deep it is. Full many the flower of sweetest fragrance born in a desert is a waste. Suppose a precious stone is made into ornament and in the hands of our Didi, Mother Didi, a ring. It is beautiful. If it is there, nobody cares for that one. Similarly, the flower with the sweetest fragrance, if it is there in a small kid head, that is beautiful. Similarly, if you are a human being, you should be an engineer. If you are an engineer, you should be a chemical engineer. And if you are a chemical engineer, you should be a member of IIChE. And if you are ChemCon, otherwise it is waste. Your life is waste. The ChemCon 2023 was successful in all ways. Heritage has maintained its prestige, right? Each and every corner, the students were there, the volunteers were there to help. The management gave us that is, us means IIChE, the greatest support, and it went well. Day and night they worked. Hats off to you all, sir. Pradeep Kumar here, sir. Okay, and all that members of the heritage, Ajit Ghosh, Vasant Chaudhary sir, Arvind ji, and all other people. Though I am did my MTech program in Jadavpur University, all my friends used to talk in English. That is the biggest problem, right? Because this fellow doesn't understand. Even if he says something, he says all nonsense in the Bengali. So let us talk in. So since those people they talk in Bengali quite often, no, I do catch up all the things. But only thing I catch up, no. Ami heritage ko balabashi. Am I right, sir? Yes, you are. Right? Okay. Thank you. I thank the organizers for giving me this opportunity. I expect the same cooperation to be extended in the ChemCon 2024. Thank you very much for the opportunity. Thank you.
I request University Chairman once again. He forgot to mention. Actually, there a slip from my side. I'm sorry for that. We express our deep sense of gratitude to all the distinguished speakers who kindly graced the symposium and part of deliberation. We also thank few of the distinguished speakers who could not come because of the last minute engagement. We are thankful to them also. We are thankful to all the delegates. We are thankful to all the invitees. We are thankful to our co-partner, Calcutta University, Jadavpur University, and also IICHE headquarters. So again, I express my slip, and it was unintentional. Thank you very much.
Yes, that I can mention that. Yes, so Rajiv Gandhi Institute of Petroleum and Technology, JIS, also associated. So special thanks to the RJIPT and their team. So I would mention Professor Sanjay Kar, who was also helping me all the way. Whenever we discuss, we three people we are discussing most of the times. So my regards to Sanjay Kar, sir, please convey from ChemCon team. So now I request our respected CEO, sir, the Heritage Group of Institution, to address. Say, sir. Okay, so thank you. And already everyone spoke about his leadership and the planning of this ChemCon. Everything is guided by him only. So thank you once again. And now I request our President-elect to address the audience, Mr. Sunil Thakurji.
Friends, the last leg of any competition or activity is most difficult. So I request you to bear with for a few more minutes and then you will be allowed to go. So, respected dignitaries on the dais, my fellow council members, invitees, students, my dear students, ladies and gentlemen. With a lot of pleasure and gratitude, starting from Almighty to seniors, fellow council members, up to all IIChE members, I accept my election win for IIChE president. The title brings in lot of responsibility to maintain sustainability and definitely to grow the institute beyond. I promise to fulfill my duties, and for that I bank upon active support of my team, council members, office staff, and as such all RCs and student chapters for total devoted support to go ahead and include more and more activities, horizons for IIChE so as to reach to each and every student chapters and regional centers as well as industries. Feel free to send your suggestions, constructive suggestions anytime, and we'll review and implement whatever possible. About the arrangements here, I have no words. Everything was so fantastic. We came on 26th and days passed and we were looking whether how can this be so perfect. We were looking for some here and there, something here and there, but could not find anything. It is so meticulously planned. I am not naming individuals, but excellently planned, be it be event management, be it be transportation, be it be accommodation, be it be our facilities or hospitality, anything, be it be catering. See, after this event, tomorrow some of us will be going to Sundarban, and the tigers of Sundarban will be definitely indebted if we come close to them for our 4 days catering arrangements. Definitely. So it was an excellent catering arrangement taste, variety, ambience, cleanliness, whatever you name. So everything is good. About this institute, I would say that I am very much impressed, not only me, my fellow council members and everybody whomsoever I talked with. Excellent arrangement, cleanliness is maintained everywhere, gardening, everything in neat and clean. Apart from that, what impressed me most is I was just talking with one of the staff members and all that, and I came to know that the equal importance is here they give to the art and culture also. See, normally other colleges we visited so many institutes, but there I find that academics is important. That there is due weightage. Some weightage is given to sports also everywhere, but here apart from these two, they have a lot of stress on art and culture. So, and it was evident in the cultural programs every day. You say you a lot of charm and gracefulness, all the dance girls who dance here and all the programs very neatly planned and executed. So we were very much impressed with that. Of course, uh, when I was trying to find some problem in the organization, I could not find any. But yes, one of the this cultural program drama, I could find one. So I told them that it was in a Bangla language. So I told them that you should have just given some summary of that, and we would have understood it more better. So, but then they explained me about the circumstances. One of the actor, drama main, Pramod, I suppose. Yeah, he the lead role who played this the main person. He was away from the station, and it was taken overnight by the other person who played that role. And hats off to him that he played it in such a way that expression wise. Execution, excellent execution. You name it as expressions or acting or the execution, whatever you say. But it was excellent. Like we never felt that it is a replacement. So my congratulations and appreciation to whole team and especially to Pramod. Friends, my lastly, I will say that our future chemical engineers sitting there are well versed and they are preparing well for taking the batons from the senior ones. It is said that make no mistake. It is said to all the gray haired people, including me. They say that make no mistake about why these babies are here. They are here to replace us. So, students, you be ready for replacing all of us, including Professor Padma Shri Professor Yadav. You work hard and be there. So, my best wishes. Only thing I would advise you that you attend all the programs, all the technical programs especially, and get updated. Some of the sessions I found the presence little less, but future you see that you get updated maximum and take the benefit of the opportunities. Thank you very much.
So thank you, Thakurji. So he is basically finance minister of this ChemCon. So please put a big round of applause for the Thakurji. Without him, nothing would happen. So thank you, sir, for your support and guidance. So before going to the president address, I just take some of the comments from the delegates. If you please pass your comments, any criticism will be well accepted. And so that most important for us. Whatever we did, we should get feedback from the audience. Yeah. Yes, sir. Sir, thank you, sir. Saxonaji, please.
No, please, sir. No.
Anyone participants? Yes, please.
to everyone. I hope I'm audible. The mic is working fine. My name is Deepika Rao and I'm from IIT Jalandhar. I came that's why because in 2024 IIT Jalandhar is going to the venue. That's why I came. And the program for the 4 day, it is a well planned, well managed. And as a student, when we come for the conference, we first saw the food should be good. Breakfast is very good, lunch is also very good and delicious, and the sweets, I must say, they are too good. Where I came from the Uttar Pradesh and I just compare the dishes, they are too delicious. As a student, we definitely find these things are too good. And the panel discussions, the themes which were chosen is on the point, and it is a demand of the present time and for the future. And I also feel that because I'm a PhD student, I thought I should say that, and I work under Dr. Nitai Bhasak from the Department of Biotechnology. So the objectives and the themes very well. I don't have too much paraphrases, but all over it is a marvelous, delicious lunches and very well learning sessions. And when I'm giving my presentations and listening to the other specialists, invited speakers, it is a very good thing. And we learned a lot. What are the different kinds of the work is going on in the research communities and what research minds think in a very broad way. We get a lot of things from these four hold. I must say that. And I also visited too many places in the Kolkata and I utilizes the time as well. So this is a very beautiful place to visit, and I hope I will again come back and enjoy the same. Thank you.
Yes, Adultab ji.
Hello.
Volunteer, can you?
Respected dignitaries on the dais, of the dais, respected teachers, my beloved students, outstanding students, presenters here. At the outset, my heartiest congratulations to all the team. Really outstanding arrangements. Food was really amazing, outstanding, and especially lectures. The lectures by starting from M.M. Sharma ji, then G.D. Yadav ji. In fact, I am not exaggerating. After attending the session of M.M. Sharma ji, G.D. Yadav ji, I really feel myself that ye really both bada feast. Attending the session was like a feast for me. I am not exaggerating. And I have my best friend, my Guruji, one of the senior IRS officers, who also attended G.D. Yadavji's session as well as M.M. Sharmaji's session. He is really thrilled and he came all the way once again to attend here. My sincere thanks, appreciations, and may I request senior IRS officer who also worked in Mumbai, several places, and he really realized that I am not exaggerating, G.D. Yadav sir, that I have written 6 books. In almost all books, I have referred your quote as God is a chemical engineer. And wherever I go to industry, wherever I try to explain, they are really thrilled and they are really got energized to say that the statement God is a chemical engineer is really true, because whether it is IC engine, internal combustion engine, external combustion engine, the electronics, instrumentation, all the way chemical compounds are there. It may be organic compounds, inorganic compounds. So that's how the existence of God is there. That's how I presented all the way. Thank you so much, sir, for really enriching all of us, really making chemical engineers proud. Thank you so much. Once again, my sincere congratulations to all the team, especially to Abhijit Ghoshji. Whenever I send, because I am there in the national organizing member also, whenever I send the updates, on the sponsorship collection or any other particular things to Abhijit ji. Even at midnight, 12 o'clock, I send 12 o'clock, 12:01, I get the reply. This is how he has been working with a lot of commitment, passion, creativity, diversity, and drive. Hearty congratulations, all of you. Thank you so much.
So we had many foreign participants, so I request Professor Kobo, can you share your feelings?
Yeah, thank you. First of all, I want to say good evening, everybody here present. My name is Professor Kobo Abdul Salam. I'm from Nigeria, one of the foreign delegates. I came in here with a colleague, Professor Manasseh, and I want to just speak on one very important observation throughout this conference. It was initially very tasky, thinking of coming all the way from Abuja to Calcutta. And Dr. Gosh here made everything easy for us. In fact, he was so meticulous that the process of getting our visa from Nigeria was very easy, because every time we contact him, either through email or through WhatsApp, he responds within 2 minutes, 3 minutes, I get a response. So it makes the process of getting the visa and all the arrangement very easy. The accommodation was provided for right from, we already know where we're coming to stay, right from Nigeria. We already know the transportation process was easy for us. When we came into the country and we flew into Calcutta, a member of the LOC was on ground to receive us, and it makes our stay easy and very comfortable. I mean, the food was fine. This is my first time in India and in Calcutta. I was afraid of the food initially, but when I started tasting the food, oh, it was not. I don't want to finish eating the food. So thank you so much. I really enjoyed my stay, and I also think my colleagues here do enjoy their stay in Calcutta. We hope that in future, maybe the next conference in 2024, we will come in more numbers. In fact, I interacted with one of the LOC member of the 2024 ChemCon, and I promised him that I'm going to advertise the flyers to our chemical engineers in Nigeria. We also have Nigeria Society of Chemical Engineers, and we do have our conferences every year. So I intend to publicize the forthcoming conference to our audience in Nigeria. So thank you for the opportunity to be in this conference.
Thank you, William.
Good afternoon, myself P.S. Mishra. I did my BTech this year from IIT Suratkal, and nice to see Vidya Shetty ma'am from IIT Suratkal here. So when I gone to convocation to IIT Suratkal this year, I talked to PhD scholar of Vidya Shetty ma'am. So I know that Vidya Shetty ma'am will be coming. She told me. So nice to see the arrangements done here for the different sessions. The sessions were divided very well for the different topics, and various speakers from the different topics in the halls were there. And managing this is not very easy to bring speakers from different topics in the different sessions, and very well managing the sessions. And the food was also very good here, and I attended this ChemCon previous year also. So seeing this Shastri sir and Abhijit Ghosh sir managing that, so previously time it was also very well managed. So thank you very much.
So thank you. So I request Professor Bala sir. So, yeah. Okay. So Saxena ji, now your turn.
दोस्तों, ये समय तो गुड इवनिंग गुड आफ्टरनून का है, पर
जिस हिसाब से ये केमकॉन 23 हुआ, मेरे को सुप्रभात कहने का मन हो रहा है, गुड मॉर्निंग। रियली इस केमकॉन 23 ने इंडियन इंस्टीट्यूट ऑफ केमिकल इंजीनियर्स में एक नई जागृति जान फूकी। अभी तक जो रिकॉर्ड हुआ, आई थिंक दैट वी वर थिंकिंग कि शायद किसी भी तरीके से 800 लोगों के डेलीगेट का रजिस्ट्रेशन होगा। आई थिंक दैट दिस हेरिटेज इंस्टीट्यूट में जो हमारा प्लेटिनम जुबली केमकॉन का आगाज हुआ था, आज उसको सफल किया और 1400 रजिस्टर्ड डेलीगेशन हुए। आई थिंक दैट इज ए रिकॉर्ड। और प्रदीप जी ने जिस तरह से अपने गाइडेंस में इस चीज को टोटल मैनेज किया टेक्निकली, मैं कह रहा हूँ, नॉट दैट इज ए हॉस्पिटलिटी इज अनदर, टेक्निकल पेपर्स, टेक्निकल प्रेजेंटेशंस, पोस्टर्स, द सीक्वेंस, द जितने भी लेक्चर्स, केमकॉन डिस्टिंग्विश्ड स्पीकर्स, अवार्ड्स के जो थे, उसका लेवल काफी ऊंचा हुआ। आई थिंक दैट दे जो अभी तक हम लोगों ने, मेरे जैसे यादव साहब ने कहा कि वो 87 से है, मैं भी 2000 से आज 23वां केमकॉन लगातार अटेंड किया है मैंने, ठीक है, एंड आई गिव इट नंबर 1, ओके। और मैं चाहता हूँ कि जिस तरह से सब लोगों ने, आप लोगों ने मिल करके केमकॉन को इंस्टीट्यूट ऑफ केमिकल इंजीनियर्स के लिए काम करके सबको प्रोत्साहित किया है, आगे में भी इसी तरह से करिएगा। और जैसा कि यादव साहब ने कहा है कि देयर इज अ वेरी ब्राइट फ्यूचर फॉर केमिकल इंजीनियर्स। आई थिंक दैट हमें उसको याद रखना है और काम करना है। अबाउट द हॉस्पिटलिटी और व्यवस्थाओं के बारे में तो मैं सिर्फ 3 ही चीज कहूँगा कि इट इज अनवेस्ट, बोलिए, ओके, ओके, इट्स प्राउड फॉर मी कि यादव साहब ने मुझे कहा कि चॉइस के अंदर सारे लोगों को डेलीगेट्स को टाई देना है। On behalf of my company, Bhumista Infra Services, I declare that we will be giving tie to everyone. Okay? And अभी आपका आ रहा है सर, आप तो अभी बेटा आपके चरणों बाकी देने वाला है सबको। तो मैं चॉइस में बंसल साहब लिख लीजिएगा, सबसे पहला इनपुट फ्रॉम भूमिस्ता that we will be sponsoring the T-shirt for all the delegates, number 1. तो प्रदीप जी टाई देंगे सर, टाई दे रहे हैं, ओके, आई एम गिविंग टाई टू एवरीवन, ठीक है, एंड विद द बेस्ट डिजाइन। और आई थिंक दैट द टाई इज डिजाइन्ड बाय प्रोफेसर डी यादव। अगेन इट्स ए यूनिक स्पेशल प्रिंटिंग जो पीरियोडिक टेबल की है। इट रिमाइंड्स द केमिकल इंजीनियरिंग एंड he did it, even color also, yes. Okay, I will make it to fit it into the system. जैसे भी टाई है, मैंने टी शर्ट के अंदर भी लोगो साइड में वगैरह कुछ किया है, we will design it और I will take a services of Abhijit who did it a lot of things. दोनों सर, बहुत छोटा आदमी हूँ मैं, मीडियम स्मॉल स्केल वाला, क्या, पर फिर भी आई ओके, यादव साहब के वचन का, उनका कहा मेरे लिए एक आदेश होता है, विल ट्राई टू डू इट, ओके सर, ओके। तेरा तुझको अर्पण किया लागे मेरा, क्या, जो कुछ है वो आप ही से कमाया है मैंने, आप ही से फिजिकल कमाई जिसको कहते हैं, आर्थिक, एकेडमिक सेशन में प्रतिष्ठा, जो भी कहा जाए। आई एम सिंपली ग्रेजुएट, बट और बड़ा मुश्किल लगता है प्रोफेसर लोगों के सामने बोलने का। जो आपने जैसे बोला कि ओनली 8% इंडस्ट्री से लोग हैं, तो मैं तो वैसे ही बड़ा घबराता हूँ कि प्रोफेसर लोगों के सामने तो बोलने में पता नहीं कितनी गलतियाँ होंगी। पर आपने मुझे इस लायक बना दिया कि जायज पे आकर के मैं बोल सकूं, तो अरे कोई बात नहीं। तो प्रदीप जी, इट्स अनमिक्स्ड, unequal and unfair, the arrangement side. So, so now I request Mr. Biswanath Chattopadhyay ji, is the Vice Chairman National Organizing Committee, and he is the person who edited all these 4 days newspaper what we publish every day. So under his leadership, with the help of the Media Science Department of Heritage Institute of Heritage Media Science Department, and all the team has done very well work. So I request sir, please. Say something. Thank you, Vijay. First of all, I stay in Calcutta, but not really directly associated with this year's ChemCon, since I did the last year's ChemCon, and kind of thought that this year I will take rest. But heritage has a different magnetic, so I just sucked in and in and in and in. Pradeep Agrawal ji, Vasav Chaudhary ji, good friend, Santosh ji, Arvind ji, Abhijit. I just, every weekend I was here and meticulously planning and everything. I enjoyed working with them, and I hope that in future also our association will continue in whichever capacity, not ChemCon. No, sir, so really I'm grateful. But I think behind how many volunteers are sitting behind? So, all, yeah. Thank you very much. I think whoever are the guests or delegates in this ChemCon, they will go back with happier memories because of all of you. And you are really the brand ambassador of heritage. I've already told Mr. Agarwal to throw a party for the volunteers, and it must be done every ChemCon as a mandatory affair, that we encourage the students that they should participate and they should be more hospitable. Thank you. And yes, oh yes, they will definitely. I think that many more will be there. They are all busy with their activities now. And and this newsletter, I thought that since it's a 4 days affair, and people should know and engage themselves by seeing something new happening, or some content should be there. And I thank Barnali, who was coordinating with me every night. I used to write editorials at 12 o'clock at night, and she was after me, please send it just to go for print. So really, the team, media science team, I indebted to them that they could make such a good effort. And for the first time in ChemCon, we have this newsletter. And thank you, everybody. Thank you, IIChE, again co-opting me for a council this time. And I think this is the last time. I think please ensure that. So well, next year also I'll be working with Mr. Jha and Mr. Bansal for Jalandhar 2024 ChemCon. And wish you a very happy New Year, and thank you very much. So thank you. And I would request Mr. Devasis Ghosh, who had worked with me last 6 months. Every work I used to share with him, and he also under his initiative we started that exhibition planning. And initially we thought 50, then come down to 15, then again come up to the 25. So this was his initiative what we started. And sir, please.
Ladies and gentlemen, I was not actually prepared. I was just sitting over there, just talking to our CSC secretary. And then suddenly I heard that Abhijit calls my name. Well, I'm really very nervous because on the dais, so many dignitaries are there. Especially, I'd like to thank the present president, Anil Sarvaji, who has always been a guiding factor for us. Then IIChE-CHEMCON, whom I first met at this place in one of our co-committee meetings. And then, of course, none but not the least, Pradeep ji. In fact, I got like Chattopadhyay sir said, I also got involved because Pradeep ji said, because I happen to know him for last 6 years. So he said, you please be here, you be in this event, because alone Avijit cannot or may not be able to handle it. And of course, the support from all of, Jadavji, I met him first during my centenary, our chemical department centenary in February. So that was the first introduction, and it was quite mesmerizing to hear you there. And of course, in this ChemCon. And the other council members, Sulilji, we kept on interacting for last 3 to 4 months over phone, on I think on virtual meetings, Karthikeyanji, Rajanandanji, and all the council members, and of course, Professor Bala, who used to call me, early in the morning, around 7:45, 8 o'clock, for the last, I think, 3 to 4 weeks, finalizing the panel members, the speakers, and lastly, the tension he gave me, I think, 3 days back. 3 serious speakers, you have to do it something, Bosch, you have to do something. Then we managed, and I think we pulled it off very well. And last but not the least, I'd like to thanks our CRC chairman, Sri Kollan Basu, who is also part of the, the organizing subcommittees, Sri IIChE-CHEMCON, our secretary, and of course myself, my other role, apart from the organizing committee of ChemCon, I'm also the treasurer of Calcutta Regional Center. So it gives me a huge pleasure and privilege to be part of this 75th or 76th ChemCon, which is also part of the Platinum Jubilee Celebration Year ChemCon. Thank you so much. Thank you all the volunteers. In fact, all the volunteers who are standing, Shumujit, and the girls out there who sometimes used to get very tensed because I used to get tensed myself because Abhijit has used to give me all the tensions to me. So it's been a pleasure, sir. Thank you so much, all the dignitaries on the dais. I enjoyed so much, and of course, Vikramji. I met him. I met his son at his office. When we discussed how the local organizing committee, the chairman sir has instructed us that how the role of power cooling towers can also be part of the sponsor associates in ChemCon. Thank you so much. Thank you all. God bless and have a very happy new year. I enjoyed so much this ChemCon, I guess all of you as well. Thank you so much.
Thank you once again. So yes, I also thanks to the CRC chairman, secretary, and other member also CRC EC members. They have worked that Dr. Sanjeev Verma is also EC member. He worked as a transport coordinator along with our Manjur Rahmanji. So now, sir, I request our principal, sir, sir, please say some few words, and then I'll call president, sir. Please, because under his guidance also, it was very fruitful to work, and we did all sorts of arrangement. He used to take update, what is happening, what is there. So I try to get all those information and give it to the sir. Then sir take it to, it's a suggestion given to me. I incorporated, try to incorporate all those suggestions. So sir, please, sir.
So friends, good afternoon to all of you or good evening to all of you. We have on the dais very distinguished people. I am not going to name each one of them. Some very distinguished people of the dais, past presidents, the present presidents, and immediate past presidents, president-elect, NOC chairman and LOC chairman, everyone. LOC chairman is the chief guest and the chief executive officer of this particular organization where I work. I am very thankful to the organizing secretary for in the 4-day event. He is now calling me to speak for 2 minutes, and I'm very happy about that. Thank you very much. It has been a very wonderful event. And in the year between 2006 to 2010, I was very deeply associated with the Indian Institute of Chemical Engineers, and I always felt that in order to keep the organization moving, it is my philosophy. It is my philosophy that in order to keep the organization moving, people who have already served should make way for people who will serve. So that was my philosophy, and I did not want to go to IIChE afterwards, because I thought that the same people going together, there is always a source of vested interest, and that creates problem for the organization. That is my belief, and I am just sharing that belief. Earlier also I shared that belief. Anyway, this ChemCon in the year 2007 was very successful, and I knew that this year's ChemCon 2023 will be very successful, and we have done that. Thanks to all of you. If there is any small mistake that is there, we are owning up that mistake. Professor M.M. Sharma was telling me, I did my PhD with Professor M.M. Sharma, and he was telling the other day that you must own up your mistake. So if there is any mistake, I am owning up the mistake as the principal of this particular organization and the senior director of this organization. I am very thankful to my students who have done a wonderful job. It is great to hear that the students are doing well, and the students are better than the teacher. The students are better than the teacher. I always say that when the students are taking over and doing better, that is the best possible thing in that teacher's life. So, you have done so well, and it is, my heart really fills up with a lot of pleasure when I hear that you have done so well. Thank you very much. And thanks to all of you, those who have come from within the city of Kolkata, from those who have come from outside the city of Kolkata, and those who have come from abroad. You have made us proud. We always say, Pitri Devo Bhavo, Matri Devo Bhavo, Acharya Devo Bhavo, and Otithi Devo Bhavo. You were our guests. And thank you very much for being guests. Thank you very much for bearing with us. Thank you. Thanks to all of you, you and your families. Stay happy, be very happy. Ultimately, happiness is the key to your good life, and I'm sure you will have that. Finally, Happy New Year 2024 to all of you. Thank you very much.
Thank you, sir.
So now I request CEO sir, just 1 minute if you can say, because everyone spoke. So
thank you, dignitaries on the dais and off the dais. I think all the success should go to the subcommittees. So under ChemCon 23, we created several subcommittees, whether it is infrastructure committee, reception committee, the hospitality committee. So all the committee worked very hard, and we more or less meeting every week, online and offline. So I would like to congratulate, apart from, yes, Heritage did something, we all coordinated actually from that. And whatever from at Heritage we do with a heart. And I would like to also thank to my school, the Heritage School, who gave their dining hall, because initially it was not planned in that way. Mrs. Chatterjee know about this. We planned this site to the college canteen, but they had offered their space for dining and VIP zone. I think everybody enjoyed, and even they gave us Sodexo. So earlier we planned for a catering agency outside. We shortlisted 3 or 4, but finally we gone for Sodexo International, because they are one of the best in the country, as well as they hosted London Olympics earlier. So they are one of the best. I think that is you all satisfied. I'm very happy. And I would like to thank all of you, those who have joined as a delegates, and all the student volunteers, my Sodexo team, and this organizing team of this the entire decoration, audio visual. There are 4 video cameras. They are assembling, and the entire event is live, so you can watch anywhere from the world. So thank you very much, and I extend my heartiest greetings for the new year. Happy New Year to all of you.
2024. Thank you.
Thank you very much, sir. So now I request our President, Professor Anil Kumar Sarvaji, to address in this vote of valedictory.
Nothing much to say after 1.5 hours. So, respected dignitaries on the dais, dignitaries of the dais, ladies and gentlemen, and my beloved students. I also organized ChemCon in 2019 and I know how much effort it takes to organize a ChemCon. For organizing the things on such a mega event, the wheels start rolling maybe months back, maybe years back. The organizing team, they have done a wonderful job and everything was running so smooth that it looked like a well-oiled machinery. Maybe good infrastructure, delicious food. I said that बहुत दिनों बाद भरपेट खाना खाया and we had good cultural evenings by Resonance and Anubhav. If there has been any inconvenience to any of the delegates, it is unintentional and I take the full blame of it. And I seek apology for that. It was totally unintentional. If any inconvenience to any of the delegates, I take the entire blame on me, entire fault on me. Then coming to the volunteers, I'll just take 2 minutes. My journey with IIChE started in 1997 when ChemCon Golden Jubilee was held in IIT Delhi. I participated in that ChemCon 1997 Golden Jubilee ChemCon as a volunteer. And in Platinum Jubilee, I'm here. And I hope when IIChE celebrates its century year in 2047, I will again be here. Because God is a chemical engineer and he cannot be cruel to another chemical engineer. So, I started my journey with IIChE in 1997, then I was inducted into EC of NRC as treasurer, then joint secretary, and I was elected council member first time in 2009. I was appointed honorary editor for ICE, Indian Chemical Engineer, the flagship journal of Indian Institute of Chemical Engineers. And during that tenure, we were fortunate to get signed with this Taylor and Francis UK for printing, publishing, and promoting our journal. And we are continuing with that also. So, not to take much of your time, I'll just give 2 messages to my fellow chemical engineers. First is, we wish that all the regional centers should be more vibrant, more dynamic. We should organize more workshops, symposiums, conferences, so that we do not have to initiate a membership drive, but the student members, they come to us, they should feel that they are losing something and they should become our members rather than restarting initial membership drive. So for that, we have to be much more vibrant on professional front. Second is, I'll request all the regional centers, I'm just deviating from the valedictory function, but 1 or 2 points I said I want to convey. They should submit their audited accounts well in time. because each year for the last 10 years or 15 years, there is an agenda item in the council. These are the centers who have not submitted their audited accounts, and then we have to take some preventive action. So I request all the regional centers to just submit their audit accounts and statement of accounts well in time, so that it does not find a mention in the council agenda items. So, nothing to take much of your time, and as I said, ChemCons have been an integral part of our chemical engineers. I think in 2047, when we celebrate Azadi Ka Amrit Mahotsav, and in that we have the centenary celebration of IIChE, I would like to see one of the volunteers as the IIChE president. And with these few words, thank you again, once again, HIT, for doing a wonderful job. It's a team job, Avijit. Good job done. ChemCon 2023, it will be history from today onwards. And it's a big challenge for Jalandhar, ChemCon 2024, to rise up to the occasion. Because they have already set up a bar. So it's a challenge. And I hope you will also come with flying colors. Thank you. Thank you very much.
Thank you very much, sir. Just we start. I'll come. So now, handing over the president medal to new president elect. So I request President Professor Anil Saravaji to hand over the president medal to Mr. Sunil Thakurji. So please. वेट सर, वेट सर, अभी शुरू नहीं हुआ, आप दे दिया तो आपको लेना भी पड़ेगा ना. So now I am requesting Vikram Sarup ji to give flower bouquet to President-elect Mr. Sunil Thakurji. And I request handing over past President medal to Mr. Anil Saravaji by Professor Mr. Sunil Thakurji. So Thakurji, please hand over the past President medal. So, as per the protocol, we had some felicitation. So, I request President Sir to felicitate the Chairman, National Organizing Committee, Professor A.S.K. Sinha. So, Sir, please. President will felicitate. No, you are not now past. No, Saravaji will do. Thakurji's tenure will start effective from 1st January. Volunteers.
Now request President sir to felicitate LOC Chairman to Mr. Vikram Sarojji. So now I request LOC Chairman sir to felicitate the President 2023 from ChemCon Organizing Committee. LOC Chairman Vikram Sarojji will felicitate President 23 Anil Sarojji. Yeah, so it's the turn of our honorary. Yeah, 8 minutes. So actually, it's the turn of our secretary now. So I take the privilege to announce for him that our Vikram Sarupji, Yadav Saab, Sinha Saab, Girwal Saab, and all the members on the dais to please felicitate our honorary secretary, Dr. Avijit. So now before the awardee's name, I just would like to give the memento to our outgoing co-opted council members. So I request President Anil Sarwaji to hand over the council memento to Professor G.D. Jadhav sir. Yes. Also hand over the memento to Mr. Vishwanath Chattopadhyay. So the co-option is yearly basis. So sir is going out again, coming in. Next, I request President sir to hand over the council memento to Professor A.S.K. Sinha sir. So we already come to the end. Before vote of thanks, I just request Bansalji to release the souvenir of ChemCon 2024. It is in the file they will share, and you can invite the dignitaries, delegates.
Namaskar and very good afternoon to all of you. Since I am the last one, it is very difficult for me to say in the end. But still, I'll take 2 minutes. Galaxy of honorable stalwarts from the various fields of chemical engineering on the dais, fellow council members, fellow chemical engineers, fellow engineers from allied disciplines, budding engineers. It was really a privilege to be here at ChemCon 2023. When a lot of others have given feedback, I really don't find words what to say new about ChemCon 2023. But I find 3 words for this ChemCon: Advitiya, Adbhut, Apratim. That is what I can say about this ChemCon. And somehow it has already been revealed that we, NIT Jalandhar, will be hosting ChemCon 2024. I'm sure my friend Dr. Abhijit Ghosh will be very relaxed as he will be relieved from the burden he was bearing on his shoulders. But I feel that burden on my shoulders now as he'll be relaxing since he is passing on baton to us. I would like to thank the council on this occasion because this is the 4th time they have imposed their faith on Doaba Regional Center at NIT Jalandhar. First ChemCon we hosted was Students ChemCon in the year 2008. Then we conducted this in a proper ChemCon in 2012, 18, and now it will be the 3rd time that we will be hosting. I understand the bars and the standards that Dr. Abhijit Ghosh and his team has raised are very high, but believe me that we will not leave no stone unturned in coming up to the expectations that each one of you have from NIT Jalandhar. A few things I would like to say at this moment that Jalandhar is a beautiful place and is a gateway to many historical, religious, and exotic places. To name a few are Golden Temple Amritsar, Pakistan border we call Wagah border or Atari border, that is nearby. Shimla Manali is not far off. Kulu Manali, again another destination. Khajiar, that is called mini Switzerland of India. Chamba and Dalhousie, they are nearby. Those who have religious interest, Vaishno Devi, Chamunda Devi, Naina Devi, Jwalaji, Kangra Devi, they are also nearby. Depends that how much time you have with us to be spent at Jalandhar. See, what I feel is that this is our collective duty to make any event successful. In this event, I have seen personally, because I chaired a session, that quality of papers were extremely good. So I would say that onus lies on everybody, on every one of us, that authors should write good papers. They should present, not only present, but to listen to the others, what they say, what they have findings, where they need corrections, or from where we can take some takeaways from our research. And likewise, industry has its own role to play. And as organizers or the host of the event, I understand that we will do our duty best and would like to come to up to your expectations. In the end, I would like to say, sir, probably 2000 onward, we were probably knowing earlier, but we came to know that God is chemical engineer. Today is reaffirmed that God is still a chemical engineer, but new dimensions have been added as far as my knowledge goes, that mother is the first chemical engineer. And in the very second day, sir said that we have been listening a very well-known commercial, Daag Achhe Hain. Prior to that, nobody ever said that ki daag bhi achhe ho sakte hain. But sir told us on the second day that accidents can be good. That was an accident on the second day of the ChemCon 2023 when we heard the words of wisdom, I would say, from the none other than Padma Shri, Padma Vibhushan, Professor M.M. Sharma, and that कि accident भी अच्छे हो सकते हैं is reaffirmed today that today we could hear Professor G.D. Yadav in this most prestigious H.L. Roy Memorial Lecture. So thank you so much for your kind words and kind insights into the entire field of chemical engineering. These few words I would like to welcome you all at NIT Jalandhar. See, I hold different positions. I'm a professor in chemical engineering. From that angle, I invite you. I'm vice chairman of this organizing committee since I was organizing secretary in 2018. So my colleague will be hosting it, but we are equally with him. I am a council member, so I take this honors to invite all of you on behalf of council as well. And I also hold an administrative position as being the registrar of NIT Jalandhar. So that is another dimension that I carry with me. So on behalf of my individual part and representing these three different dimensions, I extend a very warm welcome to all of you and look forward to welcome you at NIT Jalandhar in 2024. And for your information, the website for 2024 ChemCon is already in the air. You can log up, you can find it. It is chemcon2024.com. So time to time we shall update this website. And that's all from my side. Wish you a very happy new year 2024 and looking forward to welcome you at NIT Jalandhar. Thank you.
So now I would like to invite Divyanshu Raj and Sumit, because these two persons are here. Divyanshu, are you here? Yeah. So everyone this year using that QR code check-in process email, but it was our CEO sir first thought that you should do something in the registration process. Though I thought it may be difficulties for many people, but still the person who had worked, that is our own student from ECE, I believe, no? Second year student, and his team, 6 people are there, and they have worked within a month. They have discussed many things, whatever the problem can arise, we have discussed, and ultimately they have delivered. And most easiest way we have seen that they are coming to us to request that what are the difficulties can come. Every point, they may thought of the security point of view. I said, no, nothing will happen. Just one kit will go extra. No, sir, we can't take a risk. So they are telling that 6 layer of security process we are trying to do. So, but it is very, for me, it is very useful to work with them and see that how next time onwards we can do better. How every ChemCon can implement this. Then we thought QR code basis program schedule. It is there. Many other organizations do, but IIChE earlier they never did. And IIChE we started it. I hope that next year onward also. So I invite Divyanshu, please come, and I request our President sir to hand over the certificate for appreciation for their work. So there are another 4 people, but they could not come together. So we are giving certificate to them. So next, to acknowledge the contribution, great contribution of the various subcommittees, chairman and convener. So I request the members please come on the dais, and the certificate of appreciation I request the president and other dignitaries to hand over.
So, Mr. D.M. Butala is not here, the Finance Committee Chairman. Professor M.K. Jha, the Chairman of Publication Committee. So, Professor Pinaki Bhattacharya, sir was the Chairman of Printing Committee. Sri Vishwanath Chattopadhyay, sir, the Chairman of Registration Committee and also editor in the ChemCon newspaper. I request Santosh ji, the various subcommittees, the chairman may be one, but he act as a chairman for me in all committee. Sir, please. Professor Sulomna Chatterjee, chairman for the technical committee. Sri Sunil Thakurji, so please come, the convener of finance committee. Professor Modhu Agarwal, madam, convener of publication committee. Next, who can guess? Student Arvind Sivastamji. The convener is the convener of registration committee, but he also work in all committees. Okay. Yes, please put Dr. Obuday Malik, convener of technical committee. Lieutenant Colonel Amitabh Ghosh. So everyone told that we are disrespected. So he is the food committee and all the campus children and the campus administrator. So under his guidance, we able to make the beautiful decoration. So thank you, sir. Dr. Sanjeev Verma, convener of transport committee. Dr. Promita Sen, convener registration committee. Dr. Diptandu Datta, convener of technical committee. Dr. Doipan Sen, Dr. Aparna Rai Sarkar. Dr. Sujoy Bose, he also worked in all aspects. So whatever the job I am doing, he has helped me a lot. So Sujoy. So two certificate, what means one is I choose to request Devasisda, please come. So take one certificate, that name I correct. And Mr. Manju Raman, because he is leading the transport. This please go. So, thank you, sir. So just now I will read out the names of the awardees because we had a many number of awardees in the various technical session. Theme wise, our technical committee recommended. I told them that the theme wise one award for all days, but they told no. Every session wise and every theme wise.
So number of awardees are more. So they can collect the certificate after this program outside. Just first I am telling energy and environment theme. The awardees is M. Bala Murugan, Nalwala Madhav Bhai, Mohammad Sari, Sanam Jain, Saima Tunsi Nisa, Pawan Kumar Gupta, Gaur Prasad Bhattacharya, Antura Chaube, Swapnil Patil, Shushmit Kaur, Sriram Ashok Dixit, Ajit Kumar Prajapati, Priyanka Tripathi. Then waste and wastewater treatment, Vasinike Vishwanath, Santosh Sapna Rao, Vijay Kumar Singh, Pomi Ghosh, Drishti Bhatia, Bharat Bhushan Negi, Somen Basu, Obirami Gajendra Prasad, Parvati D. Bhatt, Neha Madi Shural, Vishwas Saini. Biochemical and Bioscience Engineering, Alamgir Ahmed, Madhurima Datta, Amar Kedia, Kumkum Kedia, Biju Jacob, Priyanka Gupta, Sarik Farim Ilai, Pranil Bhattacharya, Suparna Sen. Advanced in Chemical Engineering, Asit Kumar Saha, Pankaj Negi, Vivek Kumar Mishra, Sathi Ravaluri, Kapil Kale, Prajakta Singwam, Pramit Samanta, Shreya Banerjee, Asutosh Jadhav, Swarnojit Bhattacharya, Umang Goswami, Sudipto Chakraborty. Then advanced nanomaterial and nanotechnology, Swati M. Wadivi, Bhumika Binay, PH Sai Siddharth, Annesa Basu, Kovo As, thank you, Parama Adha, Vidya Setti, Devkrishna De, Mouli Ghosh. Transformation for energy transition, Ullas Krishnan, Kesab Kumar, Shubham Khagre, Wasin Hegre. Then advanced polymer and composite, Jayati Sharkar, Harsita Burman, Tarak Patra. These all are for oral presentation on the best paper award. Then poster presentation theme wise, energy and environment, Umesh, Shiv Kumar Sao, Sudev Das. Then transformation for energy transition, Pranav Bera, Abhishek Badami, Dev Linga Lina Sengupto, Devlina Sengupto. Advanced nanomaterial and nanotechnology, Rajnandini, Lavonni Goswami, Twamika Arti, Omalika Patro, Ashish Pandey. Then waste and wastewater treatment, Dharmadi Adhikari, Alisha Jafar, Siksa, Min Binod Rajgon, Biochemical and Bioscience Engineering, Neha Dhiman, Mili Bhomik, Annesa Chakraborty, Asmita Bagchi. Advanced Chemical Engineering, Kaushik Kundu, Srishti Priya. Advanced Polymer and Composite, Ankita Chakraborty, Protyush Bhatt, Chadbi VK Jagannath, Boja Sadhmi, Vemlu Adva Bhagre.
Nakarna Nikhala, Gunti Revant, Sai Kumar, Sasi Kumar, Sujay Raj. This name I can't read. Srishti Senne. So these all are the names, those who have selected for award certificate. You can collect after this event outside this auditorium. So just request Bala sir, please come on the stage for felicitation because he has taken a part of ChemCon very actively on the side of RGIPT and core National Organizing Committee. So I request Jadhav sir. So Bala sir, please say something.
Very good. Very good evening, and I first should thank my honorable director, Professor IIChE-CHEMCON, for giving me this opportunity. Whatever I could able to do, I tried to do for this chemical engineering society. I really feel happy about it. Nothing more than this. Wish you a very happy new year. Thank you so much. Yes, yeah. I take this opportunity to tell you all that Rajiv Gandhi Institute of Petroleum Technology is going to organize IIChE-CHEMCON 2024 in the month of September. The brochure is already out. We'll be launching the website also shortly. And on behalf of our director and on behalf of our department, I invite you all to our institute and also for IIChE-CHEMCON. Thank you so much. So I request the President sir to do the felicitation. Our Principal sir, Professor Vasav Chaudhary. Sir, please come. Yes. Sir, please, sir. Okay. So now this is my opportunity to put formal vote of thanks. Since this valedictory program, everyone already mentioned about the contribution of the various subcommittees, chairman, convener, vice chairman, other members. So I extend my heartfelt thanks to all the conveners, all the chairpersons, members. So thanks for your kind support, guidance, and help me out to get this ChemCon 23 is the grand success. So thank you all. I also extend my thanks to our respected the LOC chairman sir, CEO sir, president sir, LOC chairman sir, both the vice president, treasurer, all the council members, particularly
Some of the council members actively involved. Some of the council members are given suggestions, like Dhawal, all the way he helped me to fundraising activity with the Thakarji, Butalaji, Saxenaji. We travel Ahmedabad, Baroda, Bharuch, Ankleshwar, then Mumbai. So the total trip helped me financially sound out of this the other activities. So I thanks to everyone for helping me. And from heritage side, already we have acknowledged that I may forget, I may missed out. I apologize. Like contribution made by our GM sir, Santosh Sai ji, Colonel sir, Arvind ji, Sanjay Agarwal ji, Devasis Karmokar, Devasis Chatterjee, all the security staff, facility staff, everyone helped to give you the best facility and ease access to everywhere in the venue. So thank you all of them, and my departmental faculty members, our HOD, other faculty members, everyone worked so hard, and they have taken a lot of pain to make all the technical session so smoothly. They have completed. So thank you all of them. Other faculty members from the various departments, participants of the Heritage Institute of Technology, Heritage Group of Institution. I also extend my sincere thanks to all of them. The exhibitors, those who have put it stall, I thanks to all the exhibitors who has accepted our invitation and put their stall. Then the press media, printing media, as well as the publication houses, they have timely delivered our material and nicely covered our inaugural programs. Also, the digital media, the Telegraph, Edu Digital Partner, they have also published. So I thanks to all of them. I'd like to thanks to the event management Admode. They have done very wonderful job. So I would like to request all of you, please thanks. They have covered initially. We had a lot of discussion. I was scared. Santosh ji told, Arvind ji told, don't worry, we'll do in a day. I said, no, I can't do this. But yes, I must appreciate your hard work, and everyone complimented you through me, because they may not be knowing who are working. So everyone told such a nice branding, such a nice flex printing, digital cover, everything is very nice. So thank you for your the work. We should acknowledge. All the sponsors, like starting from Reliance, Indian Oil, Godrej, West Bengal Power Development Corporation, Aarti Industries, Haldia Petrochemical, MCPI, Bhumista Infra Services, Nelsoft, Pidilite, Waker, IPL Dhulseri, NMDC, IFRAC. So other names I can tell because I know each and every one. I have worked with them. Roopsols, then Irma. So everyone supported, and they have given due importance to IIChE-CHEMCON mostly. So this is the name of ChemCon, branding is coming, sponsorship is coming. So I thanks to all and each sponsor so for their kind support. Without their support, nothing is possible. And at the end, my team, because I am the face marks of our volunteer, so they have work basically. So the work and dedication. So people are seeing me only, but I am basically working like a mask. Behind there, our team volunteer, each and every volunteers. So I have learned many things from them also. Whenever they used to come some query, they used to tell, sir, please conduct some meeting, please sir, tell me, ask the clarification. So they used to come instead of I should tell. So thank you each and everyone for your dedication, contribution, hard work, and passion. And I told them whatever you will do with a smiling face, I hope you all have seen their smiling face only. So thank you very much. So yeah, yes, no, no. So I will call all the volunteers you told for group photo. So I request all the subcommittees, chairman, conveners, members, principal sirs, so please come on the dais, and student please come on the front. So we may have a group photo after, and we'll end. So after that we'll do the national anthem. Okay, so we'll wait, please. We'll do the national anthem, then we'll have a group photo. Okay. Yes. So I request President sir to close before national anthem the ChemCon 23.
I declare ChemCon 2023.
All council members. Okay.
DM. LS, 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 LS. Back up. LS. LS. তুই আছিস তো ডিএম এর চামচা LS.
So there is a high tea after this dining hall. So all are requested to proceed for dining hall. There is a high tea. Okay, all the volunteers and delegates are requested to go towards dining hall.
LS.
Volunteers can help themselves here, please. Some people can stand in the front side of this auditorium.
Riju, hey Riju, hey Riju, hey Riju.
শিশির
Hello. হ্যাঁ বলো।
শিশির হয়ে গেলে বলবি। रेडी सबको थोड़ा ऊपर देखना है। रेडी रेडी